You have never seen the place you live, not really. Every map, every diagram, every carefully labeled spiral galaxy poster you've ever glanced at has been lying to your brain about scale. They all show the same thing, a tiny smudge between two major arms, barely worth the ink it takes to print the name. A minor spur, a galactic footnote. The Orion Arm, they call it, and the label makes it sound like exactly what it looks like. Small, inconsequential, forgettable. Except it isn't small. It is 10,000 light-years long. It contains billions of stars, tens of billions of planets, and every single object you have ever seen in the night sky with your own eyes, every nebula in every textbook photograph, every supergiant burning its way toward collapse, exists inside it. Betelgeuse is your neighbor. The Orion Nebula is down the street. The entire night sky you grew up calling the universe is actually just one structure, one arm, one thread in a galaxy so vast that this so-called spur could swallow 1,000 human civilizations end to end and still have room left over. For decades we called it minor because we didn't have the tools to see it clearly. Then the Gaia spacecraft turned on, and what it found wasn't a spur at all. It was something denser, longer and stranger than the models predicted, a feature so large that our sense of cosmic scale had been broken from the beginning. So how did we get it this wrong? How does a structure containing everything you've ever known get reduced to a footnote on a map? And what happens when you finally see your cosmic address for what it really is? This is that story. Welcome to Magnetic Space. If you're new here, please subscribe. We make these documentaries every day, and honestly, we'd love to have you along for the ride. Before we begin, tell us in the comments where you're watching from and what time it is there. Now, settle in. This is going to be a good one. You have a cosmic address. You've probably seen it written out somewhere, maybe in a museum display or a documentary voiceover, or the caption under one of those glossy spiral galaxy posters they sell at science centers. Earth, Solar System, Orion Spur, Milky Way Galaxy, Local Group, Virgo Supercluster, Laniakea, Observable Universe. It sounds impressive. It sounds like you know where you are. And buried in the middle of that list, between the Solar System and the Milky Way proper, sits a phrase that most people glide right past without a second thought: the Orion Spur. 2 words: clean, simple, vaguely poetic. It shows up on diagrams of the galaxy as a small tick mark, a stub of material branching off one of the Milky Way's major spiral arms, like a side road peeling away from a highway. The implication is clear. The Orion Spur is minor. It's a footnote, a cosmic cul-de-sac where our solar system happens to be parked, tucked safely away from the more important, more substantial structures where the real action happens. For decades, that's been the story. Textbooks repeated it. Planetarium shows animated it. NASA illustrations color-coded it as a thin little offshoot wedged between the Sagittarius arm inward and the Perseus arm outward, neither of which we live in. We live in the gap, the in-between, the place you point to on a map when you're trying to explain to someone why Earth isn't special. Look, you'd say, we're not even on a major arm. We're out on a spur. A spur. That word does a lot of work. It's borrowed from geography, where a spur is a ridge that juts out from a mountain range, smaller than the main peaks, less significant. In the context of galaxies, a spur suggests something fragmentary, a piece that broke off, or never fully formed, or just never mattered enough to earn a real name. It's the galactic equivalent of being from a small town no one's ever heard of. The Orion Spur, in this telling, is our small town, and for a long time, no one questioned it. Why would they? The diagrams were consistent. The labels were printed in textbooks published by university presses. The models came from professional astronomers who had spent careers mapping the Milky Way's structure. If they said we lived on a spur, then we lived on a spur. End of story. Except the story was wrong. Not slightly wrong. Not wrong in some subtle technical way that only matters to specialists. Wrong in a way that completely inverts your sense of where you actually are. The Orion Arm, the structure that contains our sun and every single star you have ever seen with your naked eyes, is not a spur. It is not minor. It is not a stub, a fragment, or a galactic footnote. It is enormous. And the fact that most people still think of it as small tells you less about the structure itself and more about the limits of the diagrams we've been using to understand it. Let's start with the diagrams because that's where the lie lives. If you've ever seen an illustration of the Milky Way from above, you know what I'm talking about. The galaxy is drawn as a flat spiral, clean and symmetrical, with 4 or 5 major arms sweeping outward from a bright central bulge. The arms are thick, bold, continuous. They're colored in blue or white to represent the young hot stars that trace them. The Orion Arm, when it appears at all, is rendered as a thin line, sometimes dotted, sometimes barely visible, running at an angle between 2 of the big arms. And somewhere on that thin line, there's a tiny dot labeled "You are here." The problem is not that the diagram is inaccurate in its geometry. The problem is that it flattens the sense of scale so completely that it stops meaning anything. When you compress a structure that is thousands of light years across into a line that is a few millimeters wide on a poster, you are not communicating size. You are communicating hierarchy. You are saying visually that this thing is less important than the things drawn larger, and your brain, which is very good at reading visual weight, absorbs that message instantly. The Orion Arm looks small on the map, therefore the Orion Arm is small. Except it isn't. The Orion Arm is roughly 10,000 light years long. Some estimates stretch it to 20,000. It is somewhere in the neighborhood of 3,000 to 3,500 light years wide. To put that in terms that don't immediately slide off your brain, if you were traveling at the speed of light, the fastest speed anything in the universe can move, it would take you 3,500 years to cross it from one side to the other, not 3,500 hours, not 3,500 days, 3,500 years, the entire span of recorded human history, from the invention of writing in Mesopotamia to the smartphone in your pocket, would not be enough time for light to cross the width of the structure you live inside. And we call it a spur. We call it minor. That word minor does so much damage. It sneaks into your sense of place and deflates it. It makes you think you live somewhere unimportant, somewhere off to the side, somewhere that doesn't really matter in the grand choreography of the galaxy. And because most people never check the actual numbers, because most people reasonably assume that the experts wouldn't call something minor unless it actually was, the label sticks. You internalize it, you accept it, you move on. But here's the thing. Every star you have ever seen in the night sky is inside the Orion Arm. Every single one. Sirius, the brightest star in Earth's night sky, sitting just 8.5 light years away, inside the Orion Arm. Betelgeuse, the red supergiant in Orion's shoulder, bloated and dying, about 550 light years out, inside the Orion Arm. Rigel, the blue giant at Orion's foot, pumping out more light than 10,000 suns, inside the Orion Arm. Vega, Altair, Steneb, the summer triangle, all inside. Polaris, the North Star, reliable and steady at the end of the Little Dipper's handle, inside. Aldebaran, the eye of Taurus the bull, inside. The Pleiades, that loose glittering cluster that humans have been staring at for tens of thousands of years. Inside, when you look up on a clear night, away from city lights, and you see the Milky Way stretched across the sky like a river of faint stars, what you are seeing is not the whole galaxy. You are seeing the inside of your own neighborhood. You are standing inside a single spiral arm, looking along its length, and everything you can resolve with the naked eye is local. All of it. This is not a spur in the sense that word implies. This is not a fragment. This is a vast region of space packed with hundreds of millions of stars, and you have been living inside it your entire life without realizing how big it actually is. So why the confusion? Why has the Orion Arm been undersold for so long? Part of the answer is observational. Mapping the Milky Way is hard. You are trying to draw a map of a city while standing in the middle of it, at street level, in the fog. You can't step outside and look down from above. You can't get a clean, wide-angle view. Every star you observe is embedded in the same murky disk of gas and dust that you're embedded in, and that dust blocks visible light. For most of the 20th century, astronomers were effectively blind to large sections of the galaxy. They could map the nearby stars with decent precision. They could infer the existence of spiral arms from radio observations of hydrogen gas and from the distribution of young star clusters. But they couldn't see the full structure clearly, so they built models, educated guesses based on incomplete data. And those models, which were the best anyone could do at the time, portrayed the Orion Arm as a short spur connecting the Sagittarius Arm to the Perseus Arm, a bridge, a minor feature. The models were wrong, but they were printed in textbooks anyway because they were the best available answer. And once something gets printed in enough textbooks, it calcifies, it becomes the default. It becomes what everyone knows, even after better data starts to suggest otherwise. The second part of the answer is linguistic. The Milky Way's major spiral arms have names that sound grand. The Perseus Arm, the Sagittarius Arm, the Scutum Centaurus Arm. Those names carry weight. They sound like places that matter. The Orion Arm, by contrast, has been saddled with a rotating cast of diminishing labels. The Orion Spur, the local spur. The Orion Cygnus Arm, which at least sounds a bit more substantial, but still gets demoted to spur status in most popular references. Language shapes perception. If you call something a spur often enough, people stop questioning whether it actually is one. The third part of the answer, and this one is harder to quantify, is psychological. There is a long tradition in astronomy of making Earth and its surroundings seem less significant. The Copernican principle, the idea that we do not occupy a special place in the universe, has been one of the most productive organizing ideas in the history of science. It kept us from making the mistake of assuming the cosmos was built around us. It pushed us to look for universal laws rather than local exceptions. But somewhere along the way, the principle curdled into something else. A kind of reflexive deflation, an assumption that wherever we are must be, by definition, unremarkable. We're not at the center of the solar system. We're not at the center of the galaxy. We're not in a special galaxy. We're not even on a major spiral arm. We're out on a spur, in the galactic equivalent of nowhere. And that's exactly what we should expect because we are not special. That story is emotionally tidy. It fits a narrative that a lot of people find comforting. The idea that humans are cosmically unimportant can be freeing. It takes the pressure off. But it also means we've been primed to accept any description of our surroundings that makes them sound smaller and less interesting than they might actually be. So when someone says the Orion Arm is a minor spur, we nod along. Of course it is. What else would it be? The problem is that the data no longer supports the story. starting in the early 2000s and accelerating dramatically in the 2010s with the launch of the Gaia Space Telescope. Astronomers have been mapping the positions and motions of stars in our region of the galaxy with unprecedented precision. Millions of stars, then hundreds of millions, then over a billion. And the picture that has emerged from all that data is not the picture of a spur. It is the picture of a major structure. In 2013, a team of astronomers published results suggesting that the Orion Arm might not be a spur at all, but rather a branch of the Perseus Arm, or possibly an independent segment of spiral structure. The evidence pointed to something much larger and more organized than the old models allowed. The Orion Arm wasn't a bridge, it was a thing unto itself. That finding did not make headlines. It did not lead to a wave of corrected textbooks or updated museum exhibits. The old labels stuck because labels once applied are hard to peel off. But the evidence kept piling up. More observations, better maps, clearer pictures of how the stars in the Orion Arm are distributed, how they move, how they relate to the surrounding structures. And the more astronomers looked, the harder it became to justify calling this thing minor. Here's what makes this reversal so disorienting. You have spent your entire life thinking you lived in a particular kind of place, a quiet neighborhood, a side street, somewhere off the main drag. And it turns out you've been living in something much larger. Not at the center, no, but not in the margins either. You are inside a structure so vast that light itself would take thousands of years to cross it. A structure that contains every star your ancestors ever navigated by, every constellation they ever named, every point of light they ever wondered about. This is not a footnote. This is not a spur. This is home, and it is bigger than anyone told you. So if the Orion Arm is not a minor spur, what is it? That question does not have a clean answer yet. The debate is still running. Some astronomers argue it's a major branch of the Perseus Arm, which would make it a significant piece of one of the Milky Way's dominant structures. Others think it might be an independent arm segment, a separate feature that happens to sit between two larger arms without being subordinate to either. A third group suggests it could be part of a more complex web-like structure, where the distinction between major arms and minor spurs breaks down entirely once you look closely enough. What all three camps agree on is that the old model, the one that treated the Orion Arm as a small connector, no longer holds. The thing is too big, too well-defined, too full of stars and star-forming regions and organized structure to be brushed aside as an afterthought. The Milky Way is not as simple as the diagrams suggest, and our place in it is not as marginal as we were led to believe. Which brings us back to you, to here, to the night sky above your head. When you go outside tonight and look up, you are not looking out from some galactic backwater. You are looking out from inside one of the largest structures in your corner of the galaxy. Every photon of starlight that reaches your eye has traveled through the same immense spiral arm that you are embedded in. You are not on the edge of things, you are in the middle of them. And the fact that it has taken this long for that to become clear tells you something important about how easy it is to misunderstand your own address. The map is not the territory, the diagram is not the place, and the label, no matter how confidently it is printed, is not the truth. So what is the truth? How big is this thing really? What does it look like when you stop compressing it into a line on a poster and start measuring it star by star, light year by light year, with instruments precise enough to catch the flicker of distant suns? That is where the story gets interesting. Because once you start pulling the thread, once you start asking how big the Orion Arm actually is, you end up rewriting not just your address, but your sense of what a neighborhood even means on a galactic scale. So now you know the label was wrong. The Orion Arm is not a spur in any meaningful sense. It is not minor. It is not a stub. And once you strip away that misleading language, the obvious question surfaces. If it is not small, how big is it really? The answer depends slightly on who you ask and which measurement techniques they trust most, but the numbers cluster around a figure that keeps showing up in the literature and in radio surveys and in careful parallax measurements of young stars scattered across this region of the galaxy. 10,000 light-years. That is the working estimate for the length of the Orion Arm from end to end. Some studies stretch it to 20,000, depending on how you define the edges and where you decide the structure stops being coherent and starts blending into the surrounding interstellar medium. But 10,000 light-years is the solid, defensible, widely cited number, and it is enormous. 10,000 light-years does not fit into human intuition. Your brain has no context for it. You cannot picture it the way you can picture a kilometer or even the distance to the moon. So let's build the context piece by piece until the scale stops sliding off. Start with something familiar. Light takes about 1 1/3 seconds to travel from the Earth to the moon. That is close. That is comprehensible. You can watch a live video feed from the International Space Station, and the signal delay is barely noticeable. The moon is right there in cosmic terms. Light from the sun takes 8 minutes and 20 seconds to reach Earth, still close. If the sun exploded right now, you would have 8 minutes and 20 seconds left before the lights went out, and you would never know the difference until the moment the last photon arrived. The nearest star system beyond our own, Alpha Centauri, sits about 4 1/3 light-years away. If you left Earth tomorrow traveling at the speed of the fastest spacecraft humans have ever built, Voyager 1, currently moving at roughly 17 kilometers per second as it drifts out of the solar system, it would take you more than 70,000 years to reach Alpha Centauri. 70,000 years. The entire span of modern human civilization, from the first cave paintings in Indonesia to the smartphone in your pocket, is only about 40,000 years. You would need nearly twice that long just to reach the nearest star, and that star is 4 light-years away. The Orion Arm is 10,000 light-years long. That means if you were somehow riding a beam of light, moving at the fastest speed anything in the universe can move, it would take you 10,000 years to travel from one end of this structure to the other. Not 10,000 hours, not 10,000 days, 10,000 years. The entire history of human agriculture, cities, writing, mathematics, empires, wars, philosophy, art, science, everything humans have ever built or thought or recorded fits comfortably inside that span of time, and light crossing the Orion Arm would take exactly that long. If you tried to make the trip at human speeds, the numbers stop meaning anything. The fastest crewed spacecraft ever flown, Apollo 10, during its return from the moon, hit a top speed of about 11 kilometers per second relative to Earth. At that speed, crossing 10,000 light-years would take you roughly 26 billion years. The universe itself is only about 13.8 billion years old. You would need to live twice as long as the universe has existed just to make the trip. And that is assuming you could sustain that speed indefinitely, which you cannot, and that you did not run into anything along the way, which you would. The point is not that the trip is impossible. The point is that 10,000 light-years is so far beyond the scale of human experience that your brain treats it as effectively infinite. It is not infinite, it is a specific, measurable distance. But it is large enough that every analogy you try to use to understand it ends up sounding absurd. Here is another way to think about it. If you compressed the Milky Way galaxy down to the size of the United States, coast to coast, the Orion Arm would stretch from roughly Denver to the Atlantic Ocean. Not a side street, not a cul-de-sac, a feature spanning more than half the width of the country. That is the structure you live inside. That is the neighborhood the diagrams have been calling minor. And it is not just long, it is wide. The Orion Arm measures roughly 3,000 to 3,500 light-years across, depending on where you draw the boundaries. 3,500 light-years from one edge to the other. If you were standing at the inner rim of the arm, looking outward, and you pointed the most powerful telescope ever built at a star on the far edge, you would be seeing that star as it existed 3,500 years ago. You would be looking at light that left its source around the time the Minoans were building palaces on Crete, when Stonehenge was already ancient, when writing had just been invented in Mesopotamia. That is how wide this thing is. Now let's talk about what is inside it. Because scale is not just a question of distance, it is also a question of contents. How much stuff are we actually talking about here? The Milky Way contains somewhere between 200 and 400 billion stars. Nobody knows the exact number because counting stars in a galaxy you are embedded in is harder than it sounds. Dust blocks your view. Faint stars hide behind brighter ones. Whole regions of the galaxy are obscured from Earth's vantage point, but 2 to 400 billion is the range most astronomers agree on. It is a staggering number. More stars than there are grains of sand on all the beaches on Earth, if you believe the comparison, which gets thrown around a lot and happens to be roughly accurate. The Orion Arm does not contain all of those stars. It contains a small fraction of them. But small in galactic terms still translates to billions. Estimates vary, and no one has done a complete census, but the best guesses put the star count in the Orion Arm somewhere in the range of several billion, maybe 5 billion, maybe 10, maybe more. The number depends heavily on how faint a star you are willing to count and where you decide the arm's boundaries are. But even the conservative estimates land in the billions, billions of stars, each one a sun, each one burning hydrogen into helium, pumping out light and heat and radiation, each one with its own life cycle, its own fate, its own surrounding system of planets or debris or nothing at all. And every single one of them is inside the structure you are sitting in right now. Most of those stars are dim. Red dwarfs, small and cool and incredibly long-lived, make up the majority. They burn their fuel so slowly that some of them will outlast the universe's current age by a factor of 10. A red dwarf born today will still be shining trillions of years from now, long after the sun has died, long after every star massive enough to burn brightly has exhausted itself and gone dark. Red dwarfs are the galaxy's tortoises. Slow, steady, unremarkable, unless you are standing close enough to feel their heat. Then there are stars like the sun, mid-sized, yellow, stable, common enough that the galaxy is full of them, but rare enough that they represent only a small fraction of the total. Stars in this category live for about 10 billion years, give or take. Our sun is roughly halfway through its life. It has about 5 billion years left before it runs out of hydrogen, swells into a red giant, and incinerates the inner planets. 5 billion years. That sounds like a lot. It is not. In galactic terms, stars like the sun are sprinters. They burn bright and fast, relatively speaking, and then they are gone. And then there are the monsters. The blue giants, the supergiants, the hypergiants. Stars so massive and so luminous that they pour out more energy in a single second than the sun emits in a week. Stars like Rigel, sitting about 860 light-years away in the constellation Orion. Rigel is a blue supergiant with a luminosity roughly 120,000 times that of the sun. If you replaced the sun with Rigel, Earth would be vaporized instantly. The oceans would boil. The atmosphere would strip away. The surface would melt into a sea of molten rock. And all of that would happen in the time it takes you to blink. Stars like Rigel do not live long. They cannot. They burn so hot and so fast that they exhaust their fuel in a few million years. When they die, they do not fade quietly. They explode, supernovae. The most violent events in the universe, short of colliding black holes or neutron stars. A single supernova releases more energy in a few seconds than the Sun will emit over its entire 10 billion-year lifespan. The blast wave from a supernova can trigger the formation of new stars in nearby gas clouds. It can sterilize entire star systems. It can seed the surrounding space with heavy elements forged in the dying star's core, scattering carbon and oxygen and iron and gold into the interstellar medium, where they will eventually clump together into planets and asteroids and, on at least one known occasion, into living things. The Orion Arm contains all of these: red dwarfs by the billions, sun-like stars by the millions, massive giants and supergiants scattered throughout, burning bright and dying young. And every one of them contributes to the structure's total luminosity, its mass, its gravitational influence, its ability to hold itself together as a coherent feature across thousands of light-years of space. Now add the planets. Because stars do not exist in isolation, most of them have planets, maybe all of them. The more exoplanets astronomers discover, the more it looks like planet formation is not the exception, it is the rule. Gas clouds collapse, stars ignite, and the leftover material in the surrounding disk clumps together into planets. Rocky ones close in, gas giants farther out, ice worlds at the edges. Repeat the process a few billion times, and you end up with a galaxy full of planets. The Milky Way is estimated to contain somewhere in the neighborhood of 100 billion to 400 billion planets. Some estimates go higher. The exact number depends on assumptions about how many planets each star hosts on average, and how many of those planets are large enough to detect or matter in a statistical sense. But the range clusters around a few hundred billion. One planet for every star, give or take, maybe more. The Orion Arm, then, with its billions of stars, must contain tens of billions of planets. Again, no one has done a full census. We do not have the instruments to count every rocky world orbiting every faint red dwarf in a region thousands of light-years across. But the math is straightforward. If every star hosts even one planet on average, and billions of stars live in this arm, then tens of billions of planets must exist here. Rocky planets, gas giants, ice worlds, planets with atmospheres, planets without, planets orbiting close to their stars, tidally locked, one face eternally scorched and the other frozen, planets in wide, lazy orbits where a year lasts centuries, planets in binary systems with two suns in the sky, planets around dying stars, around newborn stars, around stars so old they have already cycled through multiple generations of planetary systems. Most of those planets are barren, hostile, radiation-blasted rocks with no atmosphere, no water, no chance of supporting life as we understand it. But some of them, statistically, must be habitable, must have liquid water, must sit in the narrow band around their star where temperatures allow chemistry to happen at a reasonable pace, must have the raw ingredients for biology, carbon, hydrogen, oxygen, nitrogen, phosphorus, must have time, stability, a magnetic field to protect against radiation, a moon to stabilize their axial tilt. All the little accidents that made Earth a place where life could not only start, but thrive and diversify and eventually build telescopes to look outward at the rest of the arm. We do not know how many of those planets exist. We do not know if any of them host life. We do not even know if life is common or rare on a galactic scale. But the sheer number of chances, the tens of billions of worlds scattered across the Orion Arm, makes it hard to believe we are the only ones. Not impossible, just hard. The more planets you add to the count, the stranger it seems that only one of them would stumble into biology. And here is the part that makes the scale even harder to grasp. The Orion Arm is not static. It is not a fixed structure sitting in place like a piece of architecture. It is dynamic, it is churning. Stars are being born inside it right now, this moment, as you sit here. Gas clouds are collapsing under their own gravity, fragmenting into clumps, heating up, igniting. Within the next million years, thousands of new stars will light up in regions of the arm that are currently dark. And within that same span of time, other stars will die. Some will fade quietly into white dwarfs, others will explode, and the debris from those explosions will drift outward, mix with the surrounding gas, and seed the next generation of star formation. This is not a museum exhibit. This is not a snapshot. This is a living system. The Orion Arm is breathing. It is cycling matter and energy on timescales that make human history look like a flicker. And you are inside it, not observing from a distance, inside, moving through it at hundreds of kilometers per second as the sun drags the solar system along its orbit around the galactic center. You are part of the system. You are made of atoms that were forged inside stars that lived and died in this arm or in arms like it billions of years ago. The iron in your blood, the calcium in your bones, the oxygen you are breathing right now, all of it came from stars. All of it was scattered into space by stellar winds or supernova explosions. All of it drifted through the interstellar medium until it clumped into a cloud that collapsed into a new star, our star, and the debris left over formed planets, one of which became Earth. You are not separate from the Orion Arm. You are a piece of it, a temporary arrangement of its atoms, a pattern that emerged briefly from the chaos of stellar evolution and planetary formation. And when you die, those atoms will return, not to the arm exactly, the timescales are too long for that, but to the Earth, which will eventually be consumed by the sun as it swells into a red giant, and the atoms that made up your body will be vaporized and scattered and maybe, billions of years from now, incorporated into something else, another star, another planet, another fleeting arrangement that might look up at the sky and wonder where it came from. So when you think about the Orion Arm, do not think of it as a place you live near. Think of it as a place you live in, a place that is 10,000 light-years long and 3,500 light-years wide, and packed with billions of stars and tens of billions of planets and clouds of gas and dust and newborn stars and dying stars and the scattered wreckage of stars that exploded millions of years ago. A place that contains every point of light your ancestors ever navigated by, every constellation, every story written about the stars, every god that ancient humans projected onto the sky, all of it inside the same structure, all of it part of the same vast, churning, dynamic spiral arm that has been carrying you through the galaxy since the moment you were born. And here is the kicker. We only figured this out recently. For most of human history, we did not even know galaxies existed. For most of the 20th century, we thought the Orion Arm was a spur, a minor feature, something you mention in passing on your way to talking about the important stuff. It has taken decades of painstaking observation, millions of measurements, and instruments sensitive enough to track the positions and motions of individual stars across thousands of light-years of space to finally understand what we are actually looking at. And the instrument that made the biggest difference, the one that rewrote the map and forced astronomers to stop calling this thing minor, is a space telescope you have probably never heard of. It does not take pretty pictures, it does not make headlines, it just measures, over and over, billions of times. And in doing so, it has given us the most detailed map of our corner of the galaxy that has ever existed. That telescope is called Gaia, and what it found changes everything. That telescope is called Gaia, and what it found changes everything. Gaia is not flashy. It does not take the kind of photographs that end up on posters or screensavers. It does not point at distant galaxies or black holes or nebulae glowing in false color. It does not hunt for exoplanets or study the cosmic microwave background or search for signs of alien life. What Gaia does is measure, over and over and over, billions of times, with a precision so absurd that it borders on the unbelievable. And in doing so, it has rewritten the map of the Milky Way more thoroughly than any instrument in history. The European Space Agency launched Gaia in December 2013. The mission's goal was simple to state and nightmarishly difficult to execute. Measure the positions, distances, and motions of as many stars as possible with enough accuracy to build a proper three-dimensional map of the galaxy. Not a rough sketch, not an educated guess based on indirect observations, a real map. One that would let you point at a star and say with confidence how far away it is, how fast it is moving, and in what direction. Before Gaia, astronomers had bits and pieces of that information for a few 100,000 stars, enough to get a rough sense of the neighborhood. Enough to know the Sun was embedded in a disc-shaped galaxy, enough to identify a few nearby clusters and star-forming regions, but not enough to see the full picture, not enough to answer basic structural questions like how many spiral arms the Milky Way has, where they are, what they are made of, or whether the Orion Arm is actually a spur or something larger. Those questions required data on millions of stars, preferably billions, and they required precision measurements of distance, which is one of the hardest things to do in astronomy. Distance is the problem, always has been. When you look at a star in the night sky, you see a point of light, that is all. The light carries information about the star's temperature, its composition, how fast it is moving toward or away from you, but it does not tell you how far away the star is. A dim nearby star and a brilliant distant star can look identical to the naked eye. Without distance, you cannot build a map. You can only build a list. The best way to measure stellar distance is an old technique called parallax. It works like this. Hold your thumb out at arm's length and close one eye. Note where your thumb appears against the background. Now switch eyes. Your thumb appears to shift. That shift, that tiny displacement, is parallax. It happens because your two eyes are separated by a few centimeters, giving you two slightly different viewpoints. The closer your thumb is to your face, the larger the shift. The farther away, the smaller. Measure the shift, know the distance between your eyes, and you can calculate how far away your thumb is. Astronomers do the same thing with stars, except instead of using two eyes separated by a few centimeters, they use two observations separated by 6 months, when Earth is on opposite sides of its orbit around the Sun. That gives them a baseline of roughly 300 million kilometers. Observe a star in January, observe it again in July, and if the star is close enough, it will appear to shift slightly against the background of more distant stars. Measure that shift, run the math, and you get the distance. The problem is that the shifts are tiny. Even for the nearest stars, the parallax angle is less than 1 arcsecond. 1 arcsecond is 1/3600th of a degree. It is the angular width of a dime seen from 4 kilometers away. For stars farther out, the parallax gets smaller, much smaller. By the time you are looking at stars a few hundred light-years away, the shift is measured in milli-arcseconds, thousandths of an arcsecond. That is the angular width of a human hair seen from 10 kilometers away. Measuring something that small requires instruments so stable, so precise, so immune to vibration and thermal drift and atmospheric distortion that for most of history it was impossible. Gaia made it possible. The spacecraft sits at a gravitationally stable point about 1.5 million kilometers from Earth, far beyond the interference of the atmosphere and the thermal noise of the planet. It carries 2 telescopes mounted at a fixed angle, feeding light into the most sensitive camera system ever sent into space. The whole spacecraft spins slowly, sweeping its field of view across the sky in a continuous looping pattern. Every star that passes through that field of view gets measured. Not once, dozens of times over the course of years. Each measurement refines the position. Each refinement sharpens the parallax. Each parallax yields a distance. The numbers are staggering. Gaia has measured the positions of roughly 1.7 billion to 1.8 billion stars, depending on which data release you are citing. 1.8 billion. That is more stars than there are people in China and India combined. More stars than there are words in all the books ever written. More stars than a human being could count in a lifetime, even if they did nothing else. And it is not just positions. Gaia's third major data release, published in 2022, included 3-dimensional positions and proper motions for almost 1.5 billion stars. Proper motion is the term astronomers use for a star's movement across the sky. Most stars move so slowly that their positions appear fixed over a human lifetime. But over decades or centuries they drift. Gaia measured that drift for well over 1 billion stars, and for a subset of 882 million stars, it provided full 6-dimensional phase space data, position in 3 dimensions, velocity in 3 dimensions. That means for nearly 1 billion stars, astronomers now know not just where they are, but where they are going. On top of that, Gaia collected spectroscopic data for 33.8 million stars. Spectroscopy is the technique of splitting starlight into its component wavelengths, the way a prism splits sunlight into a rainbow. From that rainbow, you can read the star's composition, its temperature, its rotation speed, whether it is moving toward or away from you. 33.8 million spectra. Science Telescope called it the largest ever low-resolution spectroscopic survey, largest ever. And it is not even Gaia's primary job. That is just a bonus. The mission's core breakthrough is parallax-based distance measurement, and it has given astronomers the most accurate 3-dimensional map of the Milky Way that has ever existed. For the first time, we are not guessing where stars are or inferring structure from indirect clues. We are measuring it directly, star by star, billion by billion. And when you plot all those stars, when you build a map from 1.8 billion individual data points, the galaxy that emerges does not look like the galaxy in the textbooks. It is messier, more complicated, less symmetric. The old models, the ones that showed 4 clean spiral arms sweeping elegantly outward from a central bulge, were built on assumptions that turned out to be oversimplifications. Those models were never wrong exactly. They were just incomplete, based on limited data. And once Gaia filled in the gaps, the cracks became obvious. The old spiral arm maps were built mainly from radio astronomy. In the 1960s and 70s, astronomers used radio telescopes to detect emissions from carbon monoxide and neutral hydrogen gas drifting through the galaxy. Gas is easier to map than stars in some ways, because it emits radio waves that pass through dust without being blocked. Dust, The tiny grains of carbon and silicates and frozen water that fill the space between stars is opaque to visible light, but transparent to radio. So by mapping where the gas was, astronomers could trace the spiral arms. Gas collects in spiral arms. Stars form in spiral arms. Therefore, map the gas and you map the structure. That logic was sound. It worked. It gave astronomers a rough picture of the Milky Way's layout. 4 major arms: Sagittarius, Perseus, Scutum Centaurus, Norma. A few minor arms and spurs scattered in between. Clean, symmetrical, easy to draw, easy to teach, easy to print in textbooks. The problem was that gas and stars do not always live in the same places. Gas traces star-forming regions which tend to cluster along the densest parts of spiral arms. But stars, once they form, drift. They move out of their birth clouds. They spread. Some of them get kicked by gravitational interactions with other stars or gas clouds. Some of them are born with high velocities and wander far from their origins. And older stars, the ones that formed billions of years ago, have had time to scatter all over the galaxy. Mapping the gas gives you a picture of where stars are being born. It does not give you a complete census of where all the stars actually are. Gaia does, and the picture it reveals is not a neat 4-armed pinwheel. It is a tangled, filamentary, dynamic structure that looks more like a living organism than a piece of architecture. The spiral arms are there, yes, but they are not sharp. They are not well defined. They are fuzzy. They break up into clumps and streams and clusters. They overlap. They branch. In some regions they fade out entirely. In others they split or merge. The whole structure is riddled with substructure, little knots and filaments and voids that do not fit into the old models. This is where the term flocculent comes in. Flocculent is a word borrowed from biology and chemistry, where it describes something that forms loose, irregular clumps. In the context of galaxies, a flocculent spiral is one where the arms are not grand, sweeping, continuous structures. They are patchy, made of short segments that do not connect cleanly. Some galaxies are flocculent by nature. M63, the Sunflower Galaxy, is a classic example. Its spiral arms look like they were drawn with a series of short, broken brushstrokes rather than smooth curves. The Milky Way is not fully flocculent. It does have large-scale spiral structure. But Gaia's data suggests it is more flocculent than anyone thought. The arms are not monolithic. They are collections of smaller features, and those features do not always line up the way the simplified models suggest. This is especially true for the Orion Arm. The Orion Arm in the old models was drawn as a short spur connecting the Sagittarius Arm to the Perseus Arm, a bridge, a minor feature. Gaia's data complicates that picture immediately. The stars in the Orion Arm do not form a clean bridge. They form a sprawling, irregular cloud of structure that extends for thousands of light years and does not connect neatly to either of the neighboring arms. The Orion Arm looks less like a spur and more like an independent segment of spiral structure that happens to sit between two larger arms without being subordinate to either. That is a fundamental reclassification. It changes the Orion Arm from a footnote into a major feature, and it raises uncomfortable questions about how spiral arms actually work. Are they solid structures that maintain their shape over hundreds of millions of years, or are they temporary, constantly forming and dissolving as stars and gas move through the galaxy's gravitational field? The answer, according to Gaia, seems to be closer to the second option. Spiral arms are not fixed. They are patterns, density waves that move through the galaxy like ripples on a pond. Stars pass through them, slow down briefly as they encounter denser regions, then speed up again as they emerge on the other side. The arms themselves do not rotate as solid objects. They are concentrations of stars and gas that persist because the galaxy's gravitational field funnels material into those regions and holds it there temporarily. If that is true, and it is the leading theory, then the distinction between major arms and minor spurs starts to break down. A spiral arm is just a place where enough stars happen to be concentrated at a given moment that the structure stands out against the background. How long it lasts, how well defined it is, how large it appears, all of that depends on local conditions, on how much gas is available, on how recently a burst of star formation happened, on whether a nearby supernova or stellar wind has disrupted the surrounding material. The Orion Arm, by that logic, is not minor because it is smaller. It is just one piece of a much larger, constantly shifting pattern that we are finally starting to see clearly because we can now measure where the stars actually are. And this is where Gaia's revolution becomes obvious. Before Gaia, astronomers were mapping the Milky Way the way you would map a city at night by looking at where the streetlights are. You can see the major roads, you can guess where the neighborhoods are, but you cannot see the alleys, the side streets, the empty lots, the buildings that are not lit. You are working from incomplete information. Gaia turned on every light in the city. Suddenly you can see the whole thing, and the layout is nothing like what you thought. Gaia has revealed stellar clusters that were invisible before, streams of stars torn from their parent systems by gravitational interactions, tidal tails stretching for thousands of light years where satellite galaxies are being slowly digested by the Milky Way. Shells and plumes and overdensities and voids. The galaxy is not a smooth, symmetrical spiral. It is a mess. A beautiful, organized, dynamic mess. And the more detail Gaia adds to the map, the more complex the picture becomes. One of the biggest surprises is how much substructure exists in what used to be considered empty space. Between the major spiral arms, in the regions that older maps left blank, Gaia found stars, lots of them. Not scattered randomly, but clumped into streams and filaments that trace the paths of ancient star clusters that have since dissolved, or the remnants of smaller galaxies that merged with the Milky Way billions of years ago. The galaxy is full of ghosts, structures that existed once and have since been pulled apart by tidal forces, leaving behind rivers of stars that still follow the same orbits their parent systems once traveled. Gaia can see those rivers, it can trace them, it can reconstruct what the galaxy looked like hundreds of millions or even billions of years ago by rewinding the motions of the stars and figuring out where they came from. This is not just cartography, it is archaeology, galactic archaeology. The term sounds dramatic, but it is accurate. Gaia is letting astronomers dig through the fossil record of the Milky Way, uncovering events that happened long before the Sun existed, collisions with other galaxies, bursts of star formation triggered by close encounters with neighboring systems, waves of supernovae that swept through the galaxy and reshaped the distribution of gas and dust. All of that history is encoded in the positions and motions of stars. Gaia is reading it, and the mission is not finished. Gaia is still collecting data. Every additional year of observations refines the measurements. Parallaxes get sharper, proper motions get more accurate, the map gets clearer. The European Space Agency has extended the mission multiple times because the science return is so high. As of now, Gaia has collected enough data to keep astronomers busy for decades. There are papers being published every week based on Gaia data, new discoveries, new structures, new insights into how the galaxy formed and how it is evolving. The mission has fundamentally altered the field. Science Telescope described it as having altered the astronomical playing field. That is not hype. That is an accurate assessment. Gaia changed the game. The mission's public framing, especially from the European Space Agency, emphasizes the word revolution. Revolution in astronomy. That word gets thrown around too casually sometimes. Every new telescope gets called revolutionary. Every new discovery gets hyped as paradigm shifting. But in Gaia's case, the label fits. The mission gave astronomers the tools to answer questions that were unanswerable before. It turned speculation into measurement. It replaced rough sketches with precision maps. It made the Milky Way knowable in a way it never was before. Here is the thing about revolutions. They do not just answer old questions, they create new ones. Before Gaia, astronomers argued about how many spiral arms the Milky Way had, 4 or 5 or 6. Now the question is more complicated. What even counts as a spiral arm? If the structure is filamentary, if the arms are not solid features but temporary concentrations of stars and gas, how do you draw boundaries? Where does one arm end and another begin? Those are not trivial questions. They are fundamental, and Gaia has made them urgent. The Orion Arm sits right in the middle of that debate. Is it a major feature, an independent arm segment, a large spur, a piece of a larger structure that we are still trying to identify? The old answer was simple. Spur, minor, move on. The new answer, the Gaia-era answer, is messier. It depends on what you mean by arm. It depends on how you define the boundaries. It depends on whether you are mapping gas or stars or both. And the more data Gaia provides, the harder it becomes to give a single clean answer, which brings us back to scale. Because regardless of how you classify it, the Orion Arm is enormous, 10,000 light-years long, 3,500 light-years wide, packed with billions of stars. And Gaia has shown us that it is not an isolated structure. It is embedded in a larger network of filaments and streams and clusters that extend outward in every direction. The stars in the Orion Arm are connected, gravitationally and chemically and historically, to stars in the Perseus Arm, the Sagittarius Arm, and regions farther out. The whole galaxy is a web, and every star you can see with your naked eye is part of one small corner of that web. Gaia also measured something that most people do not think about when they think about stars. It measured their radial velocities, that is the speed at which a star is moving toward or away from you along your line of sight. Combine radial velocity with proper motion and parallax, and you get full three-dimensional velocity. You know how fast the star is moving, in what direction, and where it is going. That information lets astronomers trace orbits. They can run the clock backward and figure out where stars came from. They can run it forward and see where they are headed. They can identify stars that were born together in the same cluster but have since drifted apart. They can spot stars that came from outside the Milky Way, captured during past collisions. And Gaia did not stop at stars. The mission also measured positions and motions for asteroids, comets, moons, and even distant objects like galaxies and quasars. It is not just a stellar census, it is a full sky survey. The dataset is absurdly rich. Astronomers are still figuring out what to do with all of it. The biggest takeaway, the thing that matters most for understanding where we actually live, is this. The galaxy is more complex than we thought. The Orion Arm is larger than we thought, and the map we have been using for decades, the one with 4 clean spiral arms and a few minor spurs, is not wrong exactly, but it is incomplete. It is a sketch. Gaia gave us the photograph, and once you see the photograph, you cannot go back to the sketch. So here is where we are. You live inside a structure that is 10,000 light-years long, 3,500 light-years wide, packed with billions of stars and tens of billions of planets. That structure is not a spur, it is not minor, it is a major segment of spiral structure, possibly an independent arm, embedded in a galaxy that is far more dynamic and interconnected than the textbooks suggest. And every photon of starlight that reaches your eye tonight has traveled through that structure. You are not on the edge of things, you are in the middle of them. And the map that proves it, the map that finally shows you where you are, was drawn by a single spacecraft, measuring the parallax of stars one by one over the course of a decade. Gaia rewrote the map, and in doing so, it answered one question and raised 100 more. What is the Orion Arm made of? Where did it come from? How long will it last? What shaped it? What keeps it together? Those are the questions we are only beginning to answer. And the answers, it turns out, involve more than just stars. They involve the space between stars, the voids, the bubbles, the empty regions that are not actually empty. One of those bubbles, carved out by violence millions of years ago, happens to be the one we are floating in right now. And it has a name. One of those bubbles, carved out by violence millions of years ago, happens to be the one we are floating in right now. And it has a name, the local bubble. That name sounds almost cozy, like a neighborhood park or a coffee shop you walk to on Sunday mornings. It is not. The local bubble is a cavity in space roughly 1,000 light-years across, carved out by explosions so violent they sterilized everything within reach. And you are sitting inside it right now. Here is the thing nobody tells you when they teach you about the solar system. The space around the sun is not normal. It is not representative of what most of the galaxy looks like. The interstellar medium, the thin soup of gas and dust that fills the space between stars, has an average density of about 1 atom per cubic centimeter. 1 atom. In a cube the size of a sugar cube, you would find, on average, 1 hydrogen atom. That is empty by any human standard. But it is the baseline. That is what space looks like most places in the galaxy. Thin, cold, dusty, normal. The space around the sun is not like that. The space around the sun is hot and empty. Not empty in the sense of having 1 atom per cubic centimeter, empty in the sense of having 0.001 atoms per cubic centimeter, 1,000 times less dense than the galactic average. The interstellar medium here has been evacuated, scooped out, blown away, and in its place sits a cavity filled with gas, so hot it glows in X-rays, gas that should not exist in a stable, quiet region of the galaxy, gas that can only be explained by violence. Astronomers have known about the local bubble since the 1970s, though they did not call it that at first. They called it the local hot bubble, which is more descriptive but less catchy. The discovery came from X-ray astronomy, a field that did not even exist until the 1960s, when scientists started launching rockets and satellites above the atmosphere to look at the sky in wavelengths that Earth's air blocks. X-rays do not penetrate the atmosphere. If you want to see them, you have to go to space. When the first X-ray telescopes turned on and started scanning the sky, they found X-ray sources everywhere. Distant galaxies, black holes, supernova remnants, neutron stars. All the violent, energetic objects in the universe light up in X-rays because X-rays come from gas heated to millions of degrees. That kind of temperature only shows up in extreme environments. Places where matter is being ripped apart by gravity or slammed together at relativistic speeds or blasted by radiation from dying stars. And then the telescopes found something nobody expected, a diffuse glow of X-rays coming from all directions, not from a single source, not from a distant galaxy or a supernova remnant you could point to, from everywhere. a faint background hum filling the entire sky. That should not happen. The space between stars is cold, a few tens of degrees above absolute zero. Cold gas does not emit X-rays, only hot gas does. Gas heated to at least 1,000,000 degrees, and somehow the space immediately surrounding the solar system was full of it. The initial reaction was confusion. Some astronomers thought the signal was coming from the edge of the solar system. Maybe the solar wind, the stream of charged particles constantly blowing outward from the sun, was colliding with the interstellar medium at the boundary and heating it up. That would produce X-rays, but the math did not work. The solar wind is not energetic enough to heat gas to 1,000,000 degrees, and the X-ray glow was too uniform. It was not concentrated in one direction the way you would expect if it were coming from a boundary. It was coming from all around. The next idea was contamination. Maybe the detectors were picking up noise from the spacecraft itself or from particles trapped in Earth's magnetosphere. But different missions with different instruments kept seeing the same thing. The signal was real. It was not an artifact. It was not a mistake. The space around the sun really was filled with 1,000,000-degree gas, and the only explanation that made sense was that something had heated it, something big, something violent, something that had happened a long time ago and left behind a cavity of hot, expanding gas that we were now sitting inside. That something was supernovae, plural, not one, many. Over the course of the last 10 to 20 million years, a series of massive stars in the sun's neighborhood reached the end of their lives and exploded. Each explosion released more energy in a few seconds than the sun will emit over its entire 10-billion-year lifespan. Each one sent a blast wave rippling outward at thousands of kilometers per second, plowing through the interstellar medium like a shockwave through air, and where those blast waves passed, they swept the gas and dust away, piling it up at the edges, leaving behind a cavity, a bubble. When the first supernova went off, it created a bubble maybe 50 or 100 light-years across. Hot gas in the center. Dense shell of swept-up material at the edges. Normal process. Then the second supernova exploded. Maybe a few million years later, maybe less, its blast wave expanded into a region that was already hot and already low density because of the first explosion. So it expanded faster, and it merged with the first bubble. Then a third supernova, a fourth, a fifth. Over millions of years, the bubbles merged and grew, and eventually became one large interconnected cavity with walls of dense gas and dust at the edges, and a hot, thin interior where almost all the normal interstellar matter had been blown away. That cavity is the local bubble, and the solar system is inside it, not at the center, not at the edge, somewhere in between. Current estimates place the sun fairly close to the inner rim of the bubble, drifting slowly through the interior at about 20 kilometers per second relative to the surrounding gas. That drift is not random. The sun is on a long, looping orbit around the galactic center, and over millions of years, that orbit carries it through different regions of the Orion Arm. Right now, we happen to be passing through the local bubble. In a few million years, we will drift out of it and into denser regions of the interstellar medium. In a few tens of millions of years, we might drift into another bubble, carved out by a different set of supernovae. The galaxy is full of these things. The local bubble is just the one we are in right now. Here is what 1,000 light-years means in practical terms. If you were standing at one edge of the local bubble and you shone a flashlight toward the other side, the light from that flashlight would take 1,000 years to cross the gap. 1,000 years, the entire span of the Middle Ages, from the fall of Rome to the Renaissance, would not be enough time for the light to make the trip. That is how wide this cavity is, and it is not a perfect sphere. It is lumpy, irregular, shaped by the specific locations and timings of the supernovae that carved it out, and by the pre-existing structure of the interstellar medium they exploded into. The walls are thicker in some places than others, the interior is hotter in some regions and cooler in others. But the overall structure, a cavity of low-density gas surrounded by a shell of denser material, is consistent. The evidence for the local bubble is everywhere once you know what to look for. The X-ray glow is the most direct. Satellites like ROSAT, launched in the 1990s, mapped the X-ray sky in exquisite detail and confirmed that the diffuse glow really does surround the solar system in all directions. The spectrum of that glow, the specific wavelengths of X-rays it emits, matches what you would expect from gas heated to about 1 million degrees. That is the smoking gun. Million-degree gas does not happen by accident. It happens because something exploded. Then there is the dust, or rather, the lack of it. Interstellar dust, the tiny grains of carbon and silicates and frozen water that fill the galaxy, blocks visible light. It is why you cannot see all the way across the Milky Way, even though the galaxy is transparent to radio waves and X-rays. Dust gets in the way. In most directions, if you point a telescope at a distant star, the light from that star has to pass through clouds of dust, and some of it gets absorbed or scattered. The farther away the star, the more dust in the way, the dimmer it looks. But within the local bubble, there is very little dust. The supernova blast waves swept most of it away, piling it up at the edges of the bubble, along with the gas. So when you look at nearby stars within a few hundred light-years, they appear unusually bright, not because they are intrinsically luminous, because there is less stuff in the way. Astronomers call this low extinction. It is a telltale sign that you are looking through a region of space that has been cleared out. The edges of the bubble are where things get interesting. When the blast waves from the supernova slammed into the surrounding interstellar medium, they did not just push the gas away, they compressed it, squeezed it, and when you compress gas, especially gas that is already cold and dense, you trigger star formation. The shock from a supernova can be the nudge that pushes a molecular cloud over the edge from stable to collapsing. The cloud fragments. The fragments collapse. New stars ignite. This is one of the ways the galaxy recycles itself. Old stars explode. The explosion triggers the birth of new stars. The new stars live, evolve, and some of them explode, triggering the next generation. The walls of the local bubble are lined with star-forming regions. The Orion Molecular Cloud Complex, one of the nearest and most active regions of star formation visible from Earth, sits on the edge of the bubble. So does the Ophiuchus molecular cloud. So does the Lupus molecular cloud. These are not random locations. They are there because the expanding bubble walls swept gas into those regions and compressed it enough to trigger collapse. The stars currently being born in Orion, the protostars hidden inside the nebula that Hubble and Webb have been photographing for years, owe their existence, at least in part, to supernovae that exploded millions of years ago. Cause and effect on timescales that make human history look like a blink. The age of the local bubble is uncertain, but the best estimates cluster around 10 to 15 million years. That is how long ago the first supernovae in the sequence exploded. The bubble has been expanding ever since, though the expansion has slowed over time as the blast waves lose energy and run into denser regions of the interstellar medium. Eventually, the bubble will stop expanding altogether. The gas inside will cool. Dense clouds will start to form again. And millions of years from now, the cavity will fill back in, erased by the galaxy's slow churn of matter and energy. But for now, it is still here, still hot, still mostly empty, and we are still inside it. So what does it mean to live inside a supernova-carved bubble? practically speaking, very little. The density is so low that even the densest parts of the local bubble are a harder vacuum than anything we can create in a laboratory on Earth. The million-degree gas sounds dangerous, but it is so thin that you could fly a spacecraft through it and not notice. Temperature in space does not work the way it does on Earth. Temperature is just the average speed of particles. In a gas as thin as the local bubble, there are so few particles that even though they are moving very fast, they carry almost no energy. A human body placed in million-degree interstellar gas would not burn. It would freeze, slowly, because there is nothing to conduct heat away. You would die of asphyxiation and cold long before the temperature became relevant. But the local bubble does have an effect. It shapes what we see when we look at the sky. The low density means there is very little dust between us and the nearest stars. That is why the constellations look as bright as they do. That is why amateur astronomers with backyard telescopes can see stars hundreds of light years away without needing adaptive optics or space telescopes to cut through the haze. We are living in a cleared-out region, a window. If the solar system were sitting in a denser part of the interstellar medium, the night sky would look different, dimmer, fewer visible stars, more obscuring clouds. The view we have, the one humans have been staring at for tens of thousands of years, is at least partly a result of the fact that we happen to be inside a bubble. There is also a more speculative idea, one that has not been proven but keeps coming up in the literature. Some researchers have suggested that the local bubble might have had a direct effect on Earth's climate and biosphere. When a supernova explodes within a few tens of light years of a planet, the radiation from the blast can strip away parts of the atmosphere, trigger mass extinctions, sterilize the surface. The supernovae that created the local bubble were farther away than that. The nearest ones were probably a few hundred light years out. That is far enough that the direct radiation would have been attenuated to safe levels by the time it reached Earth. But the blast waves themselves, the expanding shells of gas, can carry radioactive isotopes. Iron-60, for example. A rare isotope of iron that is only produced in supernova explosions and has a half-life of about 2.5 million years. In the late 1990s and early 2000s, scientists found traces of iron-60 in deep-sea sediment cores and in lunar soil samples. The isotope was deposited on Earth roughly 2 to 3 million years ago, and again around 7 million years ago. The only plausible source is supernova debris, a blast wave from one of the explosions that carved the local bubble swept past Earth, and as it passed, it deposited a thin layer of radioactive dust. The amounts were tiny, not enough to cause a mass extinction or sterilize the surface, but enough to be detectable, enough to leave a mark. We are living in the aftermath of those explosions. The bubble they created is our current home, and the dust they scattered is, in trace amounts, part of the ground beneath your feet and the mud at the bottom of the ocean and the rocks on the moon. That is a strange thing to sit with. You are not just inside a structure created by stellar violence. You are made in part from the debris of that violence. The atoms in your body were forged in stars. Some of those stars exploded to create the local bubble. Some of their ashes drifted to Earth. Some of those ashes were absorbed into the biosphere, cycled through oceans and soil and living organisms, and eventually assembled into you. You are not separate from the local bubble. You are a piece of it. The local bubble is also not static. It is still evolving. The hot gas inside is still expanding, though much more slowly now than it was a few million years ago. The walls are still compressing the surrounding interstellar medium, still triggering star formation in molecular clouds at the edges, and the solar system, which is not fixed in place, is drifting through it. Right now, we are moving deeper into the bubble's interior. In a few million years, we will reach a different part of the cavity. In 10 or 20 million years, we might drift out the other side entirely and into a denser, colder, dustier region of space. The view would change, the night sky would dim, molecular clouds would block more of the distant stars, and Earth, assuming it is still around and still habitable, would find itself in a very different cosmic neighborhood. But that is millions of years away. For now, the local bubble is our home. And it is not just a local curiosity, it is a piece of the larger structure of the Orion Arm. The Orion Arm is not a smooth, uniform distribution of stars and gas. It is riddled with bubbles like this one, cavities carved out by past generations of massive stars, shells of compressed gas where new stars are forming, voids where the density is so low that almost nothing exists. The interstellar medium is not a static backdrop. It is a dynamic, evolving environment shaped by the life and death of stars, and the local bubble is one of the clearest examples of that process, visible from Earth. When astronomers map the Orion Arm using data from Gaia and radio telescopes and infrared surveys, they are not just mapping stars. They are mapping structure, bubbles, shells, filaments, molecular clouds. The Orion Arm, like the rest of the galaxy, is full of this kind of substructure, and the local bubble is one node in a much larger network. It connects to other bubbles. It overlaps with expanding shells from nearby supernova remnants. It presses against the walls of molecular clouds that will, in a few million years, collapse and form the next generation of stars. The arm is not a static feature, it is a living system, and we are embedded in one small, very local part of it. There is something humbling about that. You spend your life thinking of the Earth as solid, the solar system as stable, the stars as fixed. And then you learn that the space around you is not empty. It is full of structure. Structure carved by explosions that happened before your species existed. Structure that is still expanding, still evolving, still shaping the environment your planet drifts through. You are not standing still. You are moving through a dynamic, violent, constantly changing region of the galaxy. And the fact that it looks calm from the surface of the Earth, the fact that the stars appear fixed and the sky looks stable, is an illusion of scale. On human timescales, nothing moves. On galactic timescales, everything does. The local bubble is roughly 1,000 light-years across. The Orion Arm is 10,000 light-years long. The bubble fits inside the arm the way a room fits inside a building. You live in the room. The room is inside the building. The building is inside a city. The city is on a continent. The continent is on a planet. The planet is in a solar system. The solar system is in a bubble. The bubble is in a spiral arm. The arm is in a galaxy. The galaxy is in a local group. The group is in a supercluster. And the whole stack, from the room you are sitting in right now to the edges of the observable universe, is connected, physically, gravitationally, chemically, historically. You are not separate from any of it. You are embedded in all of it. The local bubble is not the kind of thing you think about when you think about where you live. You think about your city, your country, your planet. Maybe, if you are astronomically inclined, you think about the solar system or the Milky Way. But the bubble is part of your address too. It is the immediate cosmic environment surrounding the sun, the space you are moving through, the cavity your ancestors evolved inside without ever knowing it existed. And now you do. Now you know that the space around you was carved out by explosions millions of years ago, that the stars you see are unusually bright because there is less dust in the way, that the interstellar medium here is 1,000 times thinner than average. that the hot gas filling the cavity is still glowing in X-rays, that the walls of the bubble are lined with star-forming regions where new stars are being born from the compressed debris of old ones. You know all of that now, and once you know it, you cannot unknow it. The sky does not look the same, the stars do not look fixed. You start to see the structure, the motion, the history, the fact that the universe is not a static backdrop, but a dynamic, evolving system that you are part of. That realization changes nothing about your daily life. You still have to go to work, pay bills, eat lunch, sleep. But it changes something about how you see yourself. You are not just a person on a planet. You are a temporary arrangement of atoms that were forged in stars, scattered by supernovae, assembled into a solar system, and organized into a living thing that can look up at the sky and understand, at least a little, where it came from. The local bubble is part of that story, and the stars inside it, the ones you can see with your naked eye on a clear night, are the next part. Because the Orion Arm is not just structure, it is stars, specific stars, named stars, stars with histories, stars so bright and so close that ancient humans looked at them and saw gods. And those stars are not random, they are landmarks, signposts, anchors, the brightest, most famous, most important stars in Earth's night sky, the ones that shaped human mythology and navigation and astronomy for thousands of years, are all inside the Orion Arm, all inside the same structure you are sitting in right now. And some of them are so massive, so unstable, so close to the end of their lives that they could explode at any moment. And when they do, the night sky will change. The local bubble will grow, and the Orion Arm will have one more scar carved into it by the death of a star. The local bubble is part of your address too, but it is not the only part, because 1,000 light-year cavity carved by ancient supernovae is impressive, sure, but it is still just empty space. Structure, yes. History, yes. But empty. If you want to understand what the Orion Arm actually is, you cannot just map the voids. You have to look at what fills them, the stars, the nebulae, the remnants, the objects so bright and so close and so iconic that humans have been staring at them for thousands of years without realizing they were all part of the same structure. The Orion Arm is not famous because astronomers measured it with parallax and declared it 10,000 light-years long. It is famous because it contains some of the most recognizable objects in the night sky. Stars you can name. Nebulae you can photograph with a decent backyard telescope. Remnants of explosions so violent they reshaped the surrounding space. All of it packed into a region that textbooks have spent decades calling minor. That word minor does so much damage, it makes you think the Orion Arm is a footnote, a side note, a place where nothing important happens. And then you start listing what is actually inside it, and the label falls apart immediately. Betelgeuse, the Orion Nebula, the Crab Nebula. These are not obscure objects, these are landmarks. Betelgeuse alone is one of the 10 brightest stars visible from Earth. The Orion Nebula is the nearest major star-forming region to the solar system, close enough that you can see it with the naked eye on a clear winter night. The Crab Nebula is one of the most studied supernova remnants in the history of astronomy. A textbook example of what happens when a massive star reaches the end of its life and detonates. All 3 of them are inside the Orion Arm. All 3 of them are neighbors. And all 3 of them tell a different part of the same story. The story of how stars are born, how they live, and how they die. Let's start with Betelgeuse, because Betelgeuse is the kind of star that makes people nervous. It sits in the constellation Orion, marking the hunter's right shoulder, and it is visible from almost anywhere on Earth. If you have ever looked up at Orion in the winter, you have seen Betelgeuse. It is the reddish one, the one that does not quite match the color of the other bright stars in the constellation. Rigel, at Orion's foot, glows blue-white. Betelgeuse glows orange-red, the color of a dying ember. That color is not an accident, it is a warning. Betelgeuse is a red supergiant, one of the largest stars in the known galaxy. If you replaced the Sun with Betelgeuse, the star's surface would extend past the orbit of Mars. Earth would be inside it. Venus would be inside it. Mercury would be vaporized before the swap even finished. Mars, sitting on the edge, would be skimming the outer layers of a star so bloated and so diffuse that its surface gravity is weaker than Earth's. You could, in principle, stand on the surface of Betelgeuse if it had a surface you could stand on, which it does not, and you would weigh less than you do on Earth. That should not be possible. A star more than 10 times the mass of the Sun should have crushing gravity, but Betelgeuse is so large that its outer layers are barely held together. The star is not stable. It is convulsing, pulsing, shedding mass, approaching the end. Betelgeuse is roughly 550 light-years away, give or take. That number has been refined over the years as better instruments measured its parallax and proper motion. Gaia nailed it down, 550 light-years, close enough that the star appears bright in Earth's sky, far enough that when it explodes, and it will explode, the radiation will not sterilize the planet, probably. The uncertainty there is not comforting. A supernova at 550 light-years is on the edge of what astronomers consider safe. The blast itself would not reach us. Supernovae do not send out physical debris at faster-than-light speeds. The shock wave, the expanding shell of gas, would take hundreds of thousands of years to cross the gap. By the time it arrived, humans would either be gone or so technologically advanced that a supernova shockwave would be a curiosity rather than a threat. The radiation, though, travels at the speed of light. When Betelgeuse explodes, the light from the explosion will reach Earth 550 years later. And for a few weeks or months, Betelgeuse will be the brightest object in the night sky aside from the Moon. Brighter than Venus, brighter than Jupiter, visible during the day, a new star, brilliant and white, sitting in the spot where Orion's shoulder used to be. Ancient humans would have called it an omen. Modern humans will call it the astronomical event of the millennium. And astronomers will point every telescope on the planet and in orbit at it, because a supernova this close has not been observed in recorded history. The last nearby supernova visible to the naked eye was in 1604, Kepler's supernova. It appeared in the constellation Ophiuchus and was bright enough to be seen in daylight for a few weeks. Before that, Tycho's supernova in 1572. Before that, the supernova that created the Crab Nebula in 1054, 3 supernovae in 1,000 years, all of them far enough away that they appeared as new stars rather than catastrophic explosions. Betelgeuse, when it goes, will be closer than any of them, and we will see it in detail, not just as a point of light. Telescopes today can resolve the surface of Betelgeuse as a disk, not a perfect disk. A mottled, irregular, convecting blob of gas with hot spots and cool spots and massive plumes of material being ejected into space. When it explodes, we will watch the shockwave rip through those outer layers. We will see the light curve spike and fade. We will measure the spectrum and identify every element being forged in the explosion. We will track the expanding debris field as it slams into the surrounding interstellar medium. Betelgeuse will be the most closely observed supernova in history, and it could happen tomorrow, or it could happen 100,000 years from now. We do not know. Red supergiants are unstable by nature. They are stars that have burned through all the hydrogen in their cores and moved on to helium. then carbon, then oxygen, fusing heavier and heavier elements in a desperate attempt to keep the lights on. Each new fuel burns faster than the last. Hydrogen fusion can keep a star like the Sun alive for 10 billion years. Helium fusion lasts a few 100 million. Carbon fusion lasts a few 1,000 years. Oxygen fusion lasts a few months. Silicon fusion, the last stage before the core collapses and the star detonates, lasts a few days. Betelgeuse is somewhere in that sequence, probably in the later stages, possibly in the final ones. We cannot see the core. We cannot measure what is happening deep inside. All we can do is watch the surface and wait. In late 2019 and early 2020, Betelgeuse dimmed a lot. It dropped to about 40% of its normal brightness, enough that amateur astronomers noticed with the naked eye. The internet lit up with speculation. Was this it? Was Betelgeuse about to explode? Astronomers were more cautious but still intrigued. They had been expecting Betelgeuse to go supernova eventually. This kind of dimming could be a precursor, or it could be a normal fluctuation. Red supergiants dim and brighten all the time as their outer layers expand and contract. Betelgeuse has a known cycle, but this dimming was unusually deep, too deep to ignore. Telescopes swung toward it, data poured in, and the conclusion, once the dust settled literally, was that Betelgeuse had ejected a huge cloud of gas and dust that temporarily blocked the light from the star's surface. Not a supernova, just a really dramatic burp. The cloud drifted away, the star brightened again, crisis averted. But the episode was a reminder. Betelgeuse is not stable. It is doing something, and one day, maybe soon, maybe not, it will stop doing whatever it is doing and explode. And when it does, the Orion Arm will have one more supernova remnant to add to the list. One more cavity carved into the interstellar medium. One more generation of heavy elements scattered into space. Betelgeuse is a giant among neighbors, literally. It is one of the largest stars in the local region of the galaxy, but it is not alone. The Orion Arm is full of massive stars. Rigel, the blue supergiant at Orion's foot, is another one. It sits about 860 light-years away, farther than Betelgeuse but still well within the arm. Rigel is younger, hotter, more luminous. It pours out more than 100,000 times the light of the Sun. If you replaced the Sun with Rigel, Earth would not just be vaporized, it would be ionized. The atmosphere would strip away in seconds. The oceans would flash into steam and then into plasma. The surface would melt into a sea of molten rock, and then the rock itself would start to break down into individual atoms. Rigel is not a dying star. It is a young, energetic, blindingly bright monster that will live for only a few million more years before it, too, runs out of fuel and explodes. The presence of stars like Betelgeuse and Rigel tells you something important about the Orion Arm. It is not an old, quiet, settled region. It is young, active, full of massive stars that have not had time to die yet. Massive stars do not live long. They burn hot and fast. If you see a lot of them in one place, it means star formation happened recently. Within the last few tens of millions of years, the Orion Arm is a nursery. Not in the past. Right now. Stars are being born here, today, in clouds of gas and dust scattered throughout the arm. And the most famous of those clouds, the one that has been photographed more than almost any other object in the night sky, is the Orion Nebula. The Orion Nebula sits about 1,350 light-years from Earth, smack in the middle of the Orion Arm. It is a massive star-forming region, a cloud of gas and dust, roughly 24 light-years across, glowing with the light of thousands of newborn stars. You can see it with the naked eye on a clear winter night. If you are away from city lights, look at the constellation Orion. Find the 3 stars that make up the Hunter's Belt. Below the belt, you will see a line of fainter stars running downward. That is Orion's sword. The middle star in the sword is not a star. It is the Orion Nebula, a faint, fuzzy patch of light, barely visible, easy to miss if you are not looking for it, but unmistakable once you know what you are looking at. Point a telescope at it and the view changes completely. The faint, fuzzy patch resolves into a churning cloud of gas, green and red and blue, lit from within by the light of young stars. The brightest region, the core of the nebula, is dominated by a cluster of 4 massive stars called the trapezium. These stars are less than 1 million years old, infants by stellar standards. They are so young that they are still surrounded by the remnants of the cloud they formed from. And they are so hot, so luminous, that their radiation is ionizing the surrounding gas, making it glow. That glow is what you see when you look at the Orion Nebula. It is not reflected light. It is not starlight bouncing off dust. It is the gas itself emitting light because it has been heated and ionized by the radiation from newborn stars. The Orion Nebula is loud, not in the sense that you could hear it. Sound does not travel through space, but in the sense that it is energetically violent. The trapezium stars are blasting the surrounding cloud with ultraviolet radiation. That radiation heats the gas to thousands of degrees, ionizes it, and drives it outward in a wind. At the same time, the gas is still collapsing under its own gravity in other parts of the cloud, forming new stars. The whole region is a chaotic mess of competing forces. Gravity pulling inward, radiation pushing outward, shock waves from stellar winds compressing some regions while blowing others apart. It is messy, turbulent, beautiful, and it is happening right now, in real time, in a structure that astronomers spent decades calling minor. The Orion Nebula is part of a much larger complex called the Orion Molecular Cloud Complex, which stretches for hundreds of light years and contains enough gas to form tens of thousands of stars. The visible nebula, the part you can see with a telescope, is just the tip of the iceberg. Most of the cloud is cold and dark, hidden from visible light telescopes because the gas is too cold to glow and the dust blocks the light from background stars. Infrared telescopes can see through the dust, though, and when you point an infrared telescope at the Orion Molecular Cloud Complex, you see stars, hundreds of them, thousands of them, protostars still embedded in their birth clouds, young stars just beginning to clear away the surrounding gas, all of them less than a few million years old, all of them born in the same structure. The Orion Arm is not just a place where stars live, it is a place where stars are being made. The Hubble Space Telescope has been photographing the Orion Nebula for decades, so has the James Webb Space Telescope. Webb's infrared cameras can peer deeper into the cloud than Hubble ever could, revealing protostars that are still hidden inside thick cocoons of dust. Some of those protostars are surrounded by disks of gas and dust, protoplanetary disks, the raw material that will, over the next few million years, clump together into planets. We are watching solar systems form, not in the past, not in some distant galaxy, here, in the Orion Arm, 1,350 light-years away, close enough that the light from those forming stars takes less time to reach us than the span of recorded human history. The Orion Nebula is a reminder that the galaxy is not static, it is not finished. Stars are not relics of some ancient creation event. They are being born right now in clouds like this one, scattered throughout the Milky Way. And the Orion Arm, this supposedly minor spur, contains one of the nearest and most active star-forming regions in the galaxy. That alone should disqualify it from being called minor, but we are not done yet. Because the Orion Arm does not just have stars being born, it also has stars that have died. And one of them left behind a remnant so famous, so well studied, so visually striking, that it became the first entry in the most important catalogue of celestial objects ever compiled. The Crab Nebula, Messier 1. The object that started the whole Messier catalogue, because Charles Messier, an 18th century French astronomer hunting for comets, kept finding fuzzy patches in the sky that were not comets. They did not move, they just sat there, cluttering up his search field, wasting his time. So he made a list of them, objects to ignore, things that looked like comets but were not. The first entry on that list was the Crab Nebula. Messier had no idea what it was. He just knew it was not a comet. We know better now. The Crab Nebula is the remnant of a supernova that exploded in the year 1054. Chinese and Arab astronomers recorded the event. They called it a guest star. It appeared suddenly in the constellation Taurus, bright enough to be visible during the day for several weeks. Then it faded, and for nearly 1,000 years nobody connected the guest star to the faint nebula sitting in the same part of the sky. The connection was made in the 20th century when astronomers started using spectroscopy to study the nebula's light and realized it was expanding, fast, thousands of kilometers per second. Run the expansion backward, and the whole thing converges to a single point roughly 1,000 years ago. Same location, same time. The guest star and the Crab Nebula were the same object. The star exploded. The debris expanded. And what we see today, nearly 1,000 years later, is a glowing cloud of gas and dust, roughly 11 light-years across, still moving outward, still hot, still bright, powered by a pulsar at its center. A pulsar is what is left when a massive star explodes and the core collapses into a neutron star. Neutron stars are the densest objects in the universe aside from black holes. A neutron star the size of a city weighs more than the Sun. The matter is compressed so tightly that protons and electrons are crushed together into neutrons, and the whole thing is held up not by normal atomic forces, but by neutron degeneracy pressure, a quantum mechanical effect that keeps the star from collapsing further. The neutron star at the center of the Crab Nebula spins roughly 30 times per second. Every time it spins, it sweeps a beam of radiation across space like a lighthouse. When that beam points toward Earth, we see a pulse, hence the name pulsar. The Crab pulsar is one of the most studied objects in astronomy. It is bright, it is nearby, it is stable, and it is powering the entire nebula. The energy from the pulsar, the rotational energy of a neutron star spinning 30 times a second, is being converted into radiation and particle winds that keep the surrounding gas hot and glowing. The nebula is not fading, it is not cooling. It is being continuously re-energized by the pulsar at its core, and it will stay that way for thousands, maybe millions of years, until the pulsar slows down enough that it can no longer pump energy into the surrounding cloud. The Crab Nebula sits roughly 6,500 light-years from Earth. That is farther than Betelgeuse or the Orion Nebula, but still well within the Orion Arm. The sources are cautious about this. None of them explicitly place the Crab Nebula in the Orion Arm the way they do with Betelgeuse and the Orion Nebula. But the distance fits. 6,500 light-years is within the span of the arm. And the fact that it is a supernova remnant, the debris from a star that exploded less than 1,000 years ago, tells you that this region of the galaxy is full of massive stars reaching the end of their lives. The Crab Nebula is not an isolated event. It is part of a pattern. Stars are born in the Orion Arm. They live, they die, and when they die, they leave behind remnants that reshape the surrounding space. Here is the thing that ties all three objects together. Betelgeuse, the Orion Nebula, and the Crab Nebula are not random. They are not unrelated. They are all part of the same system, the same structure, the same ongoing process of stellar evolution that has been running in the Orion Arm for millions of years and will keep running for millions more. Betelgeuse is the present, a massive star nearing the end of its life, unstable, shedding mass, waiting to explode. The Orion Nebula is the future, a cloud of gas and dust collapsing into new stars, some of which will grow up to become red supergiants like Betelgeuse and explode just like Betelgeuse will. The Crab Nebula is the past, the remnant of a star that already exploded, scattering its guts into space, seeding the surrounding interstellar medium with heavy elements that will eventually be incorporated into the next generation of stars. Birth, life, death, all of it happening in the same 10,000 light-year stretch of the galaxy, all of it visible from Earth, all of it part of the structure you are sitting in right now. And these are just the famous ones, the ones with names, the ones that show up in textbooks and planetarium shows and glossy coffee table books about space. The Orion Arm contains thousands of objects like this: nebulae, star clusters, supernova remnants, molecular clouds, stellar nurseries, dying stars. Every type of object you can find in a spiral arm, packed into a region that has been systematically undersold for decades. The word minor does not fit. It never did. The Orion Arm is not a spur in the sense that word implies. It is not a footnote. It is not a side note. It is a major feature of the galaxy. And the fact that it contains the solar system, that it contains every star you have ever seen with your naked eye, that it contains Betelgeuse and the Orion Nebula and the Crab Nebula and thousands of other objects just as interesting, should have been enough to disqualify it from being called minor decades ago. But labels stick. Once something gets printed in a textbook, it takes a long time to change. The Orion Spur, the local spur, minor spiral arm, those phrases are still in use, still being taught, still shaping how people think about where they live. And it is going to take more than a few research papers and a space telescope to dislodge them. It is going to take a shift in perspective, a willingness to look at the data and admit that the old models were incomplete, that the map we have been using is out of date, that the Orion Arm is not what we thought it was. The stars tell the story. Betelgeuse, massive and dying, a red supergiant on the edge of detonation. The Orion Nebula, glowing with the light of newborn stars, a factory churning out solar systems. The Crab Nebula, the scattered remains of a star that exploded 1,000 years ago, still bright, still expanding, still reshaping the space around it. These are not minor objects. These are landmarks, anchors, signposts, the brightest, most famous, most important stars and nebulae in Earth's night sky. And they are all inside the same structure, the structure you live in, the structure that has been carrying you through the galaxy since the moment you were born. So the next time someone tells you the Orion Arm is a minor spur, point at Betelgeuse, point at the Orion Nebula, point at the Crab Nebula. Ask them how a minor spur can contain objects that famous, that bright, that important. Ask them how a footnote can contain the birthplace of stars and the graveyard of stars and one of the largest stars in the known galaxy. Ask them how a side note can stretch for 10,000 light-years and contain billions of stars and tens of billions of planets. The answer is that it cannot. The label is wrong. The map is wrong, and the Orion Arm is not minor. It never was. It is just that we are inside it, and for a long time we did not have the tools to see it clearly. Now we do. And the picture that emerges is not the picture of a spur. It is the picture of a major spiral arm, dynamic and active and full of structure, shaped by forces that have been running for hundreds of millions of years and will keep running long after the sun dies. Forces that built the stars you see in the sky. Forces that carved the local bubble. Forces that are, right now at this moment, shaping the space you are moving through. And those forces have a name. And those forces have a name: density waves. That term does not show up in most casual conversations about space. It does not make headlines. It does not generate the kind of awe that a photograph of a supernova or a black hole generates. But if you want to understand why spiral arms exist at all, if you want to know what built the Orion Arm and what keeps it coherent across thousands of light years and millions of years, you have to understand density waves, because spiral arms are not things, they are patterns. And the difference between a thing and a pattern is everything. Here is the problem spiral arms were supposed to solve. When astronomers first started mapping the structure of other galaxies in the early 20th century, once telescopes got good enough to resolve individual galaxies as more than just fuzzy blobs, they noticed something striking. A lot of galaxies had spiral arms, clean, elegant, sweeping curves of stars and gas winding outward from a central bulge. The arms were beautiful. They were also baffling, because if you thought about them for more than a few seconds, they made no sense. Galaxies rotate. That part was obvious. The stars in a galaxy orbit the galactic center the same way planets orbit a star. Gravity pulls them inward, their motion carries them forward. The balance between the two keeps them in orbit. Fine, but galaxies do not rotate like solid objects. They rotate differentially. Stars closer to the center move faster than stars farther out. That is basic orbital mechanics. The closer you are to the gravitating mass, the faster you have to move to stay in orbit. Mercury orbits the Sun faster than Earth. Earth orbits faster than Mars. Mars orbits faster than Jupiter. Same principle. So if you have a spiral arm made of stars, and those stars are all orbiting the galactic center at different speeds depending on how far out they are, the arm should wind up, tighten, wrap around the center like a garden hose being coiled. Within a few 100 million years, maybe less, the spiral structure should blur into a featureless disk. The arms should vanish. And yet when you look at spiral galaxies, the arms are sharp, well defined, they persist. Some of these galaxies are billions of years old. They have had hundreds of galactic rotations to wind themselves up into oblivion, and they have not. The arms are still there, clean, elegant, unexplained. This was called the winding problem, and for decades it stumped everyone. The math said spiral arms should not last. Observation said they did. Something was wrong. Either the observations were being misinterpreted, which seemed unlikely given how many spiral galaxies there were and how consistent the pattern was, or the model was incomplete. Astronomers went with the second option. They started looking for a mechanism that could maintain spiral structure over long timescales without requiring the arms to be made of the same stars forever. The breakthrough came in the 1960s. Two astronomers, C.C. Lin and Frank Shu, proposed a radical idea. What if spiral arms were not made of stars at all? Not in the sense that mattered. What if the arms were not physical structures but density waves? Regions where stars and gas temporarily bunch up, slow down, and then move on. The stars would pass through the arms the way cars pass through a traffic jam. The traffic jam does not move, the cars do, but from a distance the traffic jam looks like a persistent feature. It has a location, it has a shape, it looks like a thing, but it is not a thing, it is a pattern. A temporary concentration of cars that maintains its position even as individual cars enter from behind and exit from the front. Spiral arms, Lin and Shu argued, work the same way. The arms are regions of higher density, more stars per cubic light year, more gas, more dust. Stars drift into these regions, slow down as they encounter the increased gravitational pull, spend some time in the dense environment, and then drift out the other side as they continue their orbits. The density wave itself does not rotate at the same speed as the stars. It rotates more slowly, much more slowly. So the stars move through it. And because stars are constantly entering and leaving, the arm maintains its shape even though it is not made of the same stars from one rotation to the next. This was elegant. It solved the winding problem immediately. If the arms are not material structures, they do not wind up. They are patterns imposed on the distribution of stars by the gravitational field of the galaxy. And patterns can persist as long as the field that generates them persists. The galaxy's gravitational field is not going anywhere. Therefore, the spiral arms are not going anywhere. Problem solved. The theory made predictions. If spiral arms are density waves, then stars should be moving through them. You should be able to measure that motion. You should see stars on one side of an arm moving toward it, stars inside the arm moving more slowly, and stars on the other side moving away from it. The velocities should show a clear pattern. Observers started looking, and they found exactly that. Stars near spiral arms in other galaxies showed the predicted velocity patterns. The arms were not solid, they were waves. Density wave theory was confirmed. But here is where it gets interesting. Density waves do more than just bunch up stars. They also trigger star formation. And that is why spiral arms are bright. When a cloud of cold gas drifts into a spiral arm, it encounters the density wave. The wave compresses the gas. Squeeze gas and it heats up. Heat it enough, and it can collapse under its own gravity. Collapse it, and stars form. So spiral arms are not just regions of higher stellar density, they are regions of higher star formation. And because star formation produces young, hot, massive stars, and because young, hot, massive stars are extremely luminous and extremely blue, spiral arms light up, they glow. They stand out against the rest of the galaxy, not because they contain more stars overall, because they contain more young stars. And young stars are loud. This explains why spiral arms in photographs look so distinct. You are not seeing the total stellar mass. You are seeing the most luminous stars, the ones that formed recently, the ones that will die in a few million years. Those stars trace the spiral arms because the spiral arms are where they were born. Older stars, the ones that formed billions of years ago and have since drifted out of the arms, are everywhere. They fill the disk, but they are dim. Red dwarfs and aging yellow stars do not light up a photograph the way a cluster of newborn blue giants does. So the arms appear bright and the interarm regions appear dark, even though both regions contain plenty of stars. The difference is age. The difference is luminosity. The difference is that spiral arms are where the action is. The Orion Arm fits this model. Sort of. It contains star-forming regions. The Orion Nebula, the molecular clouds scattered along its length, the young massive stars like Rigel and Betelgeuse. All of that is consistent with density wave theory. The arm is a region of enhanced density. Gas drifts in, gas gets compressed. Stars form, the stars light up the arm, the stars age and drift out. New gas drifts in, the cycle repeats, the arm persists. But there are complications. Density wave theory works best for large, grand design spiral galaxies. galaxies with 2 or 4 clean, well-defined arms that stretch all the way across the disk. Galaxies like M51, the Whirlpool Galaxy, which has 2 beautiful spiral arms that look like they were drawn with a compass. The Milky Way is not like that. The Milky Way is messier. It has multiple arms of different sizes. Some of them are major, some of them are minor. Some of them are well-defined, some of them are fragmented. And the Orion Arm, sitting between 2 major arms, does not look like a grand design feature. It looks like something else. This is where the term flocculent comes back. Flocculent spiral structure refers to galaxies where the arms are not smooth, continuous curves, but patchy, broken, irregular, made of short segments that do not connect cleanly. The term comes from the Latin word for wool or fleece, which is a polite way of saying the structure looks fluffy and disorganized. Some galaxies are fully flocculent. Their arms are so broken up that you can barely call them arms. They are more like clouds of star formation scattered loosely across the disk. The Milky Way is not fully flocculent. It has large-scale spiral structure, but it has flocculent features too. Short arm segments, spurs, branches, regions where the structure breaks down. The Orion Arm might be one of those regions. It is too large to be dismissed as random noise, too well-defined to be just a statistical fluctuation. But it does not fit neatly into the density wave picture either. If it is a density wave, it is a weak one, a secondary feature, a harmonic of the main wave. Something driven by the gravitational influence of the larger arms on either side, creating a region of enhanced density that is not quite strong enough to qualify as a major arm, but not quite weak enough to vanish. Or maybe it is not a density wave at all. Maybe it is a material arm, a real concentration of stars and gas that formed together and are moving together, not just passing through a wave. There are models that allow for this. In some simulations, spiral galaxies can have both density wave arms and material arms coexisting. The density wave arms are the big ones, the grand design features that persist for hundreds of millions of years. The material arms are smaller, shorter-lived, more dynamic. They form when a burst of star formation or a gravitational perturbation clumps stars together into a coherent structure. That structure can last for tens of millions of years before it disperses, long enough to look like a spiral arm. Not long enough to survive hundreds of galactic rotations the way a density wave arm does. The Orion Arm could be a material arm. It could be a density wave arm. It could be a hybrid. The data do not give a clean answer yet. What the data do show is that the Orion Arm is not static. It is not a fixed piece of architecture. It is dynamic. Stars are moving through it. Gas is flowing through it. The structure is evolving on timescales that are long compared to human history, but short compared to the age of the galaxy. And that evolution is driven by forces that operate on scales so vast and so slow that they are almost impossible to visualize. Here is what a density wave actually looks like if you could somehow see it. Imagine the Milky Way from above, flattened into a disk. The stars and gas are spread out across the disk, orbiting the center. Now imagine a ripple moving through that disk. Not a physical wave like a ripple on water, a gravitational wave, a region where the gravitational field is slightly stronger. As stars and gas move through that region, they slow down, not by much, just a little, enough to bunch up. The bunching increases the density. The increased density strengthens the gravitational field. The stronger field slows down more stars. The effect reinforces itself, and the result is a spiral arm, a region where the density is higher than average, maintained by the collective gravity of all the stars and gas passing through it. The wave itself does not move at the speed of the stars. It moves more slowly. In the Milky Way, stars in the solar neighborhood orbit the galactic center at about 220 kilometers per second. The density wave, the spiral pattern, rotates at maybe half that speed. So stars overtake the wave. They drift into it from behind, slow down as they pass through, and then accelerate again as they exit. The process takes tens of millions of years. A star like the Sun might spend 50 million years inside a spiral arm, then 100 million years outside, then drift into another arm. Over the course of its 10 billion year life, the Sun will pass through dozens of spiral arms, maybe more, and each time it does, the environment changes, the density increases, the radiation field gets stronger, the rate of nearby supernovae goes up. The solar system does not stay in one place. It drifts through a galaxy that is constantly reshaping itself on timescales that make geological eras look like moments. This is not speculation. Astronomers have measured the motion of stars through spiral arms in other galaxies. They have tracked the velocities. They have confirmed that stars are moving through the arms, not with them. The data are solid. Density wave theory works. It explains the persistence of spiral structure. It explains the star formation. It explains why the arms are bright. It is one of the great successes of theoretical astrophysics. But it does not explain everything. It does not explain why some galaxies have 2 arms and others have 4. It does not explain why some galaxies are grand design and others are flocculent. It does not explain the small-scale structure, the spurs and branches and filaments that fill the space between the major arms. And it does not, by itself, explain the Orion Arm, because the Orion Arm is not a major feature. It is not one of the Milky Way's dominant spiral arms. It is something in between, and in-between features are harder to model. One possibility is that the Orion Arm is a result of mode coupling. That term comes from physics and refers to what happens when 2 waves interact and produce a third wave with different properties. In a galaxy, the dominant spiral pattern is driven by 1 or 2 primary density waves, but those waves do not exist in isolation. They interact with each other. They interact with the bar at the center of the galaxy if there is one, and the Milky Way does have a bar. They interact with the dark matter halo, and all those interactions can produce secondary waves, smaller ripples, harmonics, features that are not as strong as the main spiral arms but are still coherent enough to stand out against the background. The Orion Arm might be one of those harmonics, a secondary density wave produced by the interaction between the Perseus Arm and the Sagittarius Arm. That would explain why it sits between them. It would explain why it is smaller, and it would explain why it does not quite line up with the major arms in the way a simple density wave model would predict. Harmonics do their own thing. They have their own wavelengths, their own rotation speeds, their own patterns, and they can persist as long as the primary waves that generate them persist. Another possibility is that the Orion Arm is not a density wave at all, but a kinematic feature, a structure created not by gravity but by the peculiar motions of stars and gas in this region of the galaxy. If a group of stars happens to be moving together, if they were born together in the same giant molecular cloud and are still traveling on similar orbits, they will stay clumped together for a while. That clump can look like a spiral arm even if it is not being maintained by a density wave. It is just a group of stars that have not had time to disperse yet. This kind of structure is short-lived. It lasts tens of millions of years, maybe 100 million, but that is long enough to show up in maps, long enough to confuse observers, long enough to get labeled as a spur and filed away as a minor feature. The truth is probably a mix. The Orion Arm probably has characteristics of both density wave arms and material arms. It probably has regions where the density wave is strong and star formation is active, and regions where the structure is just the leftover debris of past star formation drifting through space. It is not a clean, simple object. It is a messy, dynamic, evolving feature embedded in a galaxy that is itself messy and dynamic and evolving. And the fact that it has taken this long to figure out what it is tells you something important about how hard it is to map a galaxy from the inside. Density wave theory gives you the framework. It tells you that spiral arms are patterns, not things. It tells you that stars move through them. It tells you that the arms trigger star formation and persist over hundreds of millions of years. But it does not give you the details. It does not tell you where every spur and branch and filament comes from. It does not tell you why some regions of the Milky Way look like grand design spirals and others look like flocculent messes. And it does not, by itself, tell you whether the Orion Arm is a major feature or a minor one. What it does tell you is that the Milky Way is not a static snapshot. It is a living system. Stars and gas are constantly moving through gravitational fields that shape their distribution on scales of thousands of light-years and timescales of millions of years. Spiral arms form, persist, and dissolve. Star-forming regions ignite and fade. Supernovae carve out bubbles that reshape the interstellar medium, and the whole structure, the entire galaxy, is evolving in response to forces that have been running since the galaxy first assembled more than 10 billion years ago. Forces that built the Orion Arm, forces that are right now shaping the space around you. Here is the kicker. You are moving through a density wave right now. The solar system is inside the Orion Arm. That means it is inside a region of enhanced density. Not by a huge amount. The density in a spiral arm is only a few % higher than the density in the interarm regions. But that small difference is enough to change the environment, enough to increase the rate of nearby supernovae, enough to expose the solar system to slightly higher levels of cosmic radiation, enough to trigger bursts of star formation in nearby molecular clouds that will, millions of years from now, populate the arm with a new generation of massive stars that will live fast and die young and reshape the local interstellar medium just like the stars before them did. And in a few tens of millions of years, the solar system will drift out of the Orion Arm. It will move into the interarm region between Orion and Sagittarius. The density will drop, the radiation field will weaken, the rate of nearby supernovae will decrease. The night sky, assuming anyone is still around to look at it, will change, not dramatically, not in a way you would notice over a human lifetime. But over millions of years, the constellations will shift. The stars that currently dominate the sky will drift away. New stars will drift in, and the solar system will be in a different environment. Quieter, less active, less prone to the kind of violent events that carved the local bubble and triggered the formation of the Orion Nebula. That is what it means to live in a galaxy. You are not standing still. You are moving through structure, through density waves, through regions of high and low density, high and low star formation, high and low radiation. The galaxy is not a fixed backdrop. It is a dynamic system that you are embedded in, and the forces that shape it, the density waves that build spiral arms and trigger star formation and maintain structure over hundreds of millions of years, are the same forces that shaped the environment your planet formed in, the same forces that determined how many supernovae went off nearby in the last few billion years, the same forces that influenced the rate at which heavy elements were deposited into the molecular cloud that eventually collapsed to form the Sun. You are not separate from the density waves. You are a product of them, an emergent feature of a system that has been running for longer than your species has existed. longer than your planet has existed, longer than your star has existed. And here is the part that makes all of this almost unbearably strange. None of it matters to your daily life. You can live your entire life without thinking about density waves. You can ignore the fact that you are moving through a spiral arm. You can go about your business, work your job, raise your kids, grow old, die, and none of this will ever touch you in a way you can feel. The forces are too large. The timescales are too long. You are too small. And yet the forces are there. The structure is there. The density wave is there, right now, moving through the galaxy at a different speed than the stars, shaping the distribution of matter, triggering star formation, carving out the environment that made you possible. Density wave theory is not just an abstract piece of physics. It is the explanation for why the Orion Arm exists, why spiral arms exist, why galaxies are not featureless disks but structured, dynamic, beautiful systems that maintain coherent patterns over timescales longer than most stars live. It is the answer to the winding problem, the solution to a puzzle that stumped astronomers for decades, and it is, in a very real sense, the reason you are here. Because if spiral arms did not exist, if density waves did not compress gas and trigger star formation, the molecular cloud that formed the sun might never have collapsed. The elements that make up your body might never have been forged in the right stars at the right time in the right place. The environment that allowed Earth to become habitable might never have existed. You owe your existence, at least in part, to a gravitational ripple moving through the Milky Way at 100 kilometers per second, a density wave that has been running for hundreds of millions of years, a wave that built the Orion Arm, carved the local bubble, triggered the formation of Betelgeuse and Rigel and the Orion Nebula and the Crab Nebula and every other object in your corner of the galaxy. A wave that you are moving through right now, at this moment, as you sit here and read these words. The wave does not care, it is not conscious, it is not alive, it is just a pattern imposed on the distribution of stars by the collective gravity of 100 billion suns. But that pattern is everything. It is the structure that holds the galaxy together, the framework that makes spiral arms possible, the engine that drives star formation and maintains the cosmic environment that allowed life to arise on at least one small planet orbiting one unremarkable star in one supposedly minor spiral arm. And now you know, the Orion Arm is not minor. It is not a spur. It is a major feature of the galaxy, shaped by density waves, populated by billions of stars, stretching for thousands of light years and containing every object you have ever seen in the night sky. It is your home, your address, your place in the universe. And once you understand that, once you see the structure and the forces that built it, you cannot unsee it. The galaxy stops being a static backdrop and becomes a living system, a dynamic, evolving, structured environment that you are moving through, not passively, not as a spectator, but as a participant, a piece of the system. A temporary arrangement of atoms that were forged in stars, shaped by density waves, assembled into a planet, and organized into a living thing that can look up at the sky and finally, after thousands of years of wandering, understand where it actually is. You owe your existence, at least in part, to a gravitational ripple moving through the Milky Way at 100 kilometers per second, a density wave that has been running for hundreds of millions of years. A wave that built the Orion Arm, carved the local bubble, triggered the formation of Betelgeuse and Rigel and the Orion Nebula and the Crab Nebula and every other object in your corner of the galaxy. A wave that you are moving through right now, at this moment, as you sit here. The wave does not care. It is not conscious. It is not alive. It is just a pattern imposed on the distribution of stars by the collective gravity of 100 billion suns. But that pattern is everything. It is the structure that holds the galaxy together, the framework that makes spiral arms possible, the engine that drives star formation and maintains the cosmic environment that allowed life to arise on at least one small planet orbiting one unremarkable star in one supposedly minor spiral arm. And now you know, the Orion Arm is not minor. It is not a spur. It is a major feature of the galaxy, shaped by density waves, populated by billions of stars, stretching for thousands of light years, and containing every object you have ever seen in the night sky. It is your home, your address, your place in the universe. And once you understand that, once you see the structure and the forces that built it, you cannot unsee it. The galaxy stops being a static backdrop and becomes a living system, a dynamic, evolving, structured environment that you are moving through, not passively, not as a spectator, but as a participant, a piece of the system. A temporary arrangement of atoms that were forged in stars, shaped by density waves, assembled into a planet, and organized into a living thing that can look up at the sky and finally, after thousands of years of wondering, understand where it actually is. So let's pull it all together. Let's take everything we have learned, everything the old maps got wrong, everything Gaia revealed, everything the density waves explain, and build the picture of what the Orion Arm actually is, not what we thought it was, not what the textbooks said for decades, what it is, right now. Based on the best data humanity has ever collected, the Orion Arm is roughly 3,500 light-years wide. Some measurements push it closer to 4,000. The exact number depends on where you draw the boundaries, and boundaries in space are not sharp lines. They are gradients, regions where the density fades from higher than average to lower than average over hundreds of light years. But 3,500 light years is the working number, the one that shows up in the literature, the one Gaia's data supports. 3,500 years for light to cross from one edge to the other. The entire span of recorded human history would not be enough time for a photon to make that trip. The length is harder to pin down. Older estimates said 10,000 light years. Some sources stretch it to 20,000. The discrepancy comes from the fact that the Orion Arm does not have clean endpoints. It does not start and stop the way a road does. It fades, it branches, it merges with other structures. At some point, you have to decide where the Orion Arm ends and the Perseus Arm begins, or where it transitions into the Sagittarius Arm, or where it just dissolves into the general interstellar medium. Different researchers draw those lines in different places, but the consensus clusters around 10 to 20,000 light years. A massive structure by any measure, longer than many galaxies are wide. The Orion Arm sits about 26,000 light-years from the galactic center. That places it roughly halfway out from the center to the edge of the disk. Not in the suburbs, not in the outskirts. In the middle band, where the density is high enough to support active star formation, but not so high that the radiation environment becomes sterilizing. A sweet spot. A region where molecular clouds can collapse into stars without being torn apart by the intense radiation and gravitational forces closer to the center. A region where planets can form and remain stable for billions of years without being disrupted by close encounters with other stars or swept into unstable orbits by gravitational perturbations from the central bar. The arm is not a smooth, uniform distribution of stars. It is lumpy, clumpy, full of substructure. Bubbles carved by supernovae, shells of compressed gas where new stars are forming. Molecular clouds so dense and so cold that they block visible light completely. clusters of young stars still huddled together in the regions where they were born, streams of older stars drifting away from their birthplaces, dispersing into the general population, voids where the density is lower than average because the gas has been swept away or because no star formation has happened there recently. The Orion Arm is not a thing. It is a collection of things, a network of structures embedded in a larger pattern, and the pattern is dynamic. It is not frozen. It is not static. Stars are moving through it at hundreds of kilometers per second. Gas is flowing through it, funneled by density waves and gravitational fields. Molecular clouds are collapsing into new stars. Massive stars are exploding and scattering their guts into space. The interstellar medium is being heated by radiation, cooled by expansion, compressed by shock waves, ionized by ultraviolet light. The whole structure is churning, evolving, reshaping itself on timescales that are long compared to human history, but short compared to the age of the galaxy. Gaia gave us the map. 1.8 billion stars measured with enough precision to place them in three-dimensional space and track their motions. That is the dataset. That is the foundation. And when you plot all those stars, when you build a map from 1.8 billion individual data points, the Orion Arm that emerges is not the Orion Arm from the old textbooks. It is larger, more complex, more interconnected with the surrounding structures. It does not sit in isolation between the Sagittarius Arm and the Perseus Arm. It overlaps with them. It branches off them. It connects to them in ways the old models did not predict. The boundaries are fuzzy, the structure is messy, and the distinction between major arms and minor spurs starts to break down entirely once you look closely enough. This is where density wave theory becomes essential, because without it, the whole structure makes no sense. Why does the Orion Arm exist at all? Why does it maintain its shape over millions of years, even though the stars inside it are constantly moving? The answer is that the arm is not held together by the stars. It is held together by gravity, by the collective gravitational field of the entire galaxy. The density wave moves through the disk at a different speed than the stars. Stars drift into the wave, slow down, bunch up, and then drift out the other side. The wave persists, the stars come and go, and the result is a structure that looks solid but is actually fluid. A pattern that looks permanent but is actually temporary on galactic timescales anyway. Long enough to last hundreds of millions of years, long enough to shape the environment every star in the arm experiences. The Orion Arm is a density wave feature, probably, maybe. The data are not entirely clear. Some parts of the arm look like density waves, other parts look like material arms, regions where stars and gas clumped together and are moving together, not just passing through a wave. The truth is probably a mix. The Orion Arm is probably a hybrid structure, part density wave, part material arm, part leftover debris from past bursts of star formation. And the exact proportions of each depend on which part of the arm you are looking at and when. Here is what that means in practical terms. The Orion Arm is not a fixed piece of architecture. It is a living system. It is being built and destroyed and rebuilt continuously. Star formation happens in bursts. A molecular cloud collapses. Hundreds or thousands of stars ignite over the course of a few million years. The most massive ones live fast and die young, exploding as supernovae within 10 million years of being born. The explosions carve out bubbles. The bubbles compress the surrounding gas. The compressed gas collapses into new stars. The cycle repeats, and the whole process reshapes the local environment on timescales that are fast enough to matter, but slow enough that no individual human will ever see it. You are living inside one stage of that cycle. The local bubble is the aftermath of a burst of star formation that happened 10 to 15 million years ago. The stars that formed in that burst are mostly gone now, exploded, scattered, drifted away. But the cavity they carved is still here, still expanding, still hot, and the walls of the cavity, the shells of compressed gas at the edges, are the sites of the next generation of star formation. The Orion Nebula, the molecular clouds in Ophiuchus and Lupus, those regions are being squeezed by the expanding bubble, and the squeezing is triggering collapse. New stars are forming right now in the debris of old ones. The cycle is running, the arm is alive, and you are moving through it. The solar system is not standing still. It is orbiting the galactic center at about 220 kilometers per second. That orbit carries it through different regions of the Orion Arm over tens of millions of years. Right now, the Sun sits fairly close to the inner edge of the local bubble. In a few million years, it will drift deeper into the bubble's interior. In 10 or 20 million years, it might drift out the other side entirely and into a denser region of the interstellar medium. The environment will change, the density will increase, the radiation field will shift. The rate of nearby supernovae will go up or down depending on where the Sun ends up, and the night sky, assuming anyone is still around to look at it, will look different, not dramatically, not in a way you would notice over a human lifetime. But over millions of years, the constellations will shift. The stars that dominate the sky today will drift away. New stars will drift in. The Orion Arm will still be there, but the solar system will be in a different part of it, a different neighborhood, a different environment. This is what it means to live in a galaxy. You are not standing on solid ground. You are drifting through a structured, dynamic, constantly evolving system that operates on scales so vast and timescales so long that they are almost impossible to hold in your head. But the system is there. The structure is there. The forces that built it and maintain it are there, and they are shaping the environment you live in right now, at this moment, in ways you cannot see but can measure if you have the right instruments. Scale is everything, and scale is also nothing. Because once you understand the scale, once you wrap your head around the fact that the Orion Arm is 10,000 light-years long and 3,500 light-years wide and contains billions of stars and tens of billions of planets, the numbers stop meaning anything. They are too big. Your brain cannot hold them, but you can hold the implications. You can hold the idea that the Orion Arm is not a footnote, not a side note, not a minor spur. It is a major feature of the galaxy, a massive, structured, dynamic region that spans a significant fraction of the Milky Way's disk and contains a significant fraction of its star-forming activity. And here is the part that changes everything. The Orion Arm is not unique. It is not special. Every spiral arm in every spiral galaxy is doing the same thing, building structure, triggering star formation, carving out bubbles, cycling matter and energy through birth and death and rebirth. The Orion Arm is just the one you happen to be in, the one you can see most clearly because you are embedded in it. But the process is universal. It is happening in the Perseus Arm. It is happening in the Sagittarius Arm. It is happening in every spiral arm, in every spiral galaxy in the observable universe. Billions of galaxies, trillions of spiral arms, all of them running the same cycle, all of them shaped by the same forces: gravity, density waves, star formation, supernovae, the churn of matter through stellar lifetimes. You are not separate from that process. You are part of it. Every atom in your body was forged in a star. Every element heavier than helium was created in a stellar core or a supernova explosion. The carbon in your cells, the oxygen you breathe, the calcium in your bones, the iron in your blood, all of it came from stars. All of it was scattered into space by stellar winds or supernova explosions. All of it drifted through the interstellar medium, mixed with gas and dust, collapsed into a molecular cloud, and eventually assembled into a solar system. Your solar system, the sun, the planets, the asteroid belt, the comets. All of it built from the ashes of dead stars, and all of it happened inside the Orion Arm, or in a structure very much like it, because the Orion Arm is where the sun was born, 4.6 billion years ago, in a molecular cloud very much like the Orion Nebula. The sun formed, the planets formed, and over billions of years, one of those planets became habitable. Life started. Life evolved. Life diversified. And eventually, life produced organisms complex enough to look up at the sky and wonder where they came from. And now you know, you came from the Orion Arm, not metaphorically, literally. The atoms that make up your body were cycled through multiple generations of stars in this arm or in nearby structures. The environment that allowed Earth to remain habitable for billions of years was shaped by the density of stars and the rate of supernovae and the distribution of heavy elements in this region of the galaxy. The Orion Arm is not just your address, it is your origin, your history, your home in the deepest sense of that word. That changes your perspective. It has to. Because once you understand that you are not just living on a planet or in a solar system or in a galaxy, but that you are living in a specific spiral arm with a specific structure and a specific history, the universe stops being an abstract backdrop and becomes a place, a real place. A place with geography, with landmarks, with structure. The Orion Arm is your neighborhood. Betelgeuse is your neighbor. The Orion Nebula is down the street. The local bubble is your backyard. And the density wave that built all of it is the foundation your house sits on. And here is where it gets even stranger. The Orion Arm is not just your home. It might be home to others, not humans, not anything we have ever seen, but potentially life, other life. Because if the Orion Arm contains tens of billions of planets, and if even a tiny fraction of those planets are habitable, and if even a tinier fraction of those habitable planets actually host life, then the Orion Arm is full of living worlds. We do not know if that is true. We have exactly one data point, Earth. One planet where life started and thrived and produced a technological civilization capable of asking these questions. One planet out of tens of billions. That is not enough data to draw conclusions, but it is enough to ask the question. If life started here, in this environment, in this spiral arm, shaped by these density waves and these supernovae and this distribution of heavy elements, could it have started elsewhere, in similar environments, on planets orbiting stars in the Orion Nebula, on worlds circling red dwarfs in the local bubble, on rocky planets in the dense molecular clouds at the edges of supernova remnants? The astrobiology implications are staggering. The Orion Arm is not a quiet, empty, stable region. It is violent, active, full of radiation and supernovae and stellar winds, but it is also rich. Rich in heavy elements, rich in molecular clouds, rich in star-forming regions, rich in planets. That combination makes it a prime candidate for habitability, not in the sense that every planet is habitable, most are not, but in the sense that the conditions for life, the raw ingredients, and the environmental stability exist in abundance. The Orion Arm is a cradle, a nursery, a place where stars and planets and possibly life are being made continuously. We are looking for that life right now. Telescopes on the ground and in space are scanning nearby stars for planets. Spectrographs are analyzing the atmospheres of those planets, searching for chemical signatures that could indicate biology, oxygen, methane, combinations of gases that do not make sense unless something is producing them, something alive. We have not found anything yet. But the search is accelerating. Every year we discover hundreds of new exoplanets. Every year the instruments get better, the spectra get clearer, the data get richer. And every planet we find in the habitable zone of a nearby star is another chance, another roll of the dice, another test of the hypothesis that life is not unique to Earth but common in regions like the Orion Arm where the conditions are right. If we do find life, if we detect biosignatures in the atmosphere of a planet a few hundred light years away, it will be one of the most important discoveries in human history. It will answer a question humans have been asking for thousands of years: are we alone? And the answer will be no. We are not alone. We are part of a larger community of living worlds scattered throughout the Orion Arm, separated by distances so vast that communication would take centuries, isolated by the sheer scale of space, but connected by the fact that we all emerged from the same galactic environment, the same density waves, the same supernovae, the same molecular clouds. We are siblings, not biologically, not genetically, but cosmically, products of the same stellar nursery, shaped by the same forces. That is a profound shift in perspective, from a species that thought it lived on a minor spur in an unremarkable galaxy, to a species that understands it lives in a major spiral arm filled with structure and activity and possibly life. From a species that thought the universe was built on a hierarchy with Earth at the bottom, to a species that understands the universe is not a hierarchy but a network, a web of connections. Gravitational, chemical, historical, every star connected to every other star by the forces that shaped them. Every planet connected to every other planet by the atoms they are made of. Every living thing, if there are other living things, connected by the fact that they all emerged from the same cosmic environment. You are not at the center of that network. You are not special, but you are part of it. A node, a piece of the system. And the system is bigger and richer and more dynamic than anyone thought. The Orion Arm is not a footnote, it is a chapter, a long, complicated, still being written chapter in the story of how the Milky Way formed and evolved and continues to churn out stars and planets and possibly life, and you are living in that chapter right now, at this moment. As the solar system drifts through a density wave and the local bubble expands and Betelgeuse edges closer to detonation and the Orion Nebula churns out new stars and the whole arm evolves in response to forces that have been running for hundreds of millions of years, so here is your true cosmic address, not the one you were taught in school, not the one printed in the old textbooks, the real one. The one that captures the scale and the complexity and the dynamic nature of the structure you actually live in. Earth, solar system, local bubble, Orion Arm, Milky Way galaxy, local group, Virgo supercluster, Laniakea, observable universe. Every level of that address matters. Every level represents a real structure with real scale and real history. And the Orion Arm, sitting in the middle of that list, is not a placeholder. It is not a minor detail. It is a massive, dynamic, structured region of the galaxy that spans thousands of light years and contains billions of stars and has been shaping the environment your planet formed in since long before your species existed. When you look up at the night sky, you are not looking out at the galaxy. You are looking along the length of the Orion Arm. Every star you can see with your naked eye is inside it. Every constellation, every myth, every story humans have ever told about the stars. All of it local, all of it part of the same structure. The Big Dipper is inside the Orion Arm. Orion is inside the Orion Arm. The Summer Triangle is inside the Orion Arm. The Pleiades are inside the Orion Arm. Polaris is inside the Orion Arm. You are not looking at the whole galaxy, you are looking at your neighborhood, and your neighborhood is 10,000 light-years long. That realization does not change your daily life. You still have to get up in the morning. You still have to go to work. You still have to eat and sleep and pay bills and deal with all the mundane, grinding, unavoidable realities of being a living organism on a planet. But it changes something deeper. It changes your sense of place, your sense of scale, your sense of connection to the larger system you are embedded in. You are not a random accident on a random planet orbiting a random star in a random corner of a random galaxy. You are a product of a specific environment, a specific spiral arm, a specific network of density waves and supernovae and star-forming regions that has been running for hundreds of millions of years. You are part of the Orion Arm, and the Orion Arm is part of you. The old maps were wrong, not completely, not in the broad strokes, but wrong enough that the labels stuck and the misconception persisted. The Orion Arm is not a spur, it is not minor, it is not a footnote, it is a major feature of the galaxy, a massive, structured, dynamic region that contains every star you have ever seen and is shaping the environment your planet moves through and will continue to shape that environment for millions of years to come. That is your true cosmic address. That is where you actually are. And once you see it, once you understand the scale and the structure and the forces that built it, you cannot go back. The night sky changes. The stars stop being fixed points and become part of a living system. The galaxy stops being a static backdrop and becomes a place, a real place. A place you are moving through, a place that made you, a place that is, in every meaningful sense, home. And the best part? We are still learning. Gaia is still collecting data. The map is still being refined. The boundaries are still being redrawn. The structure is still being understood. Every year the picture gets clearer. Every year we find new clusters, new streams, new substructures embedded in the Orion Arm. Every year the old labels look more inadequate. Every year the gap between what we thought we knew and what we actually know gets wider. And every year the Orion Arm reveals itself to be larger, more complex, more important than we gave it credit for. That is the story. That is the truth. That is your true cosmic address. You live inside a structure 10,000 light-years long, carved by density waves, populated by billions of stars, shaped by supernovae, filled with molecular clouds and nebulae and star-forming regions and dying giants, a structure that contains every landmark in the night sky, a structure that made the environment your planet formed in, a structure that is, right now, evolving and churning and building the next generation of stars that will light up the galaxy millions of years from now. You are not on the edge of things. You are not in the margins. You are in the middle of one of the largest, most active, most important regions of the Milky Way. And that structure, that massive spiral arm that has been carrying you through the galaxy since the moment you were born, is not a spur, it is home. So the next time someone tells you the Orion Arm is a minor spur, you will know better. You will know that the label is a relic, a fossil from an era when the data were incomplete and the maps were rough and the instruments were not good enough to see what was actually there. You will know that the structure you live inside is 10,000 light-years long and 3,500 light-years wide and packed with billions of stars and tens of billions of planets. You will know that it contains Betelgeuse and the Orion Nebula and the Crab Nebula and every star your ancestors ever navigated by. You will know that it is shaped by density waves that have been running for hundreds of millions of years. You will know that it is carved by supernovae that exploded before your species existed. You will know that it is alive, churning, evolving, building new stars and destroying old ones, and reshaping the space around you on timescales that make human history look like a flicker. And you will know that your address, your true cosmic address, is not a footnote, it is not a side note, it is not a place where nothing important happens. It is a major feature of the galaxy, a massive spiral arm, a nursery where stars are born, and a graveyard where stars die, and a structured, dynamic, constantly evolving system that you are part of, not separate from, part of. Every atom in your body came from stars that lived and died in this arm, or in structures like it. Every breath you take is filled with oxygen forged in stellar cores and scattered by supernova explosions. You are not standing on the edge of the galaxy looking inward. You are embedded